Recording in progress.
Let's start. Good morning, everyone. Uh, Thanks for being here. I know it's been many days of lectures. My name is Alex. I will talk to you about LLM agents. Just before starting, I wanted to thank the organizers for having me. This is really nice to be able to visit Yerevan and also meet all of you and tell you about agents. So very happy to be here. So I'm Alex. I work at ServiceNow. I'm a research scientist, and I'm also affiliated to MIDA and Laval University in Quebec. Great. So I hope this is no surprise to you. AI is becoming increasingly capable, outperforming humans at various tasks. For example, this is already a long time ago. We've seen AlphaGo defeat the world champion of Go, Lee Sedol. We've seen Voyager, which is a recent model, who outperforms humans at games like Minecraft, so outperforming us in game environments. AI is becoming increasingly capable of acting in the physical world. So we have OpenAI, who made a robotic hand that is able to solve Rubik cubes. We have Waymo, who has mastered self-driving cars, basically. So you can take a taxi with no driver, and this works pretty well. And more recently, we were starting to see AI, just there's a small lag. Yeah, AI taking over the digital world, if you want, right? Controlling computers on our behalf. So this is a video from a work that's called OS World. And essentially, this is an AI model controlling many computers at the same time. Okay, so what do all of these have in common, actually? Anyone know? AI agents. Okay, so all of these applications that look like, wow, this is nice applications of AI, they're all about agents. Okay, so AI that is acting in simulated world, physical world, or more recently, the digital world. So today you will learn about how we make those kinds of AI agents. We will actually, first I'll try to introduce what an agent is, define basic concepts. Then I'll try to explain how we build, how we use LLMs to build agents. And then how we can actually take these agents and deploy them in the real world to produce kind of pretty useful applications, in my opinion. Then I'll explain how we can go beyond zero-shot agents, which means how you can train agents to be better. And I'll finish with key open problems because beyond these nice demos that you just saw, there's many, many open problems to be solved. So we'll cover those together. Okay. And by the way, if you have any questions at any time, stop me. We have plenty of time. So what is an agent? Okay, is anyone here familiar with agents? Has anyone heard about AI agents before? 1, 2, 3, 4. Whoa, many people. Okay, good. So an agent is something that perceives its environment, that's able to reflect, make decisions, and then act in the environment to optimize a goal. Okay, so essentially, if I can try to explain this with this little cartoon, basically an agent receives a goal. It has an environment in front of us, just like us right now. It perceives it in some way. So this could be through vision. It could be even through text. So it could receive a textual description of what's going on around it. It could be through various sensors, whatever. The idea is that you have to be able to perceive your environment. And then, well, it would be nice, actually. Yeah, I got you. Thank you very much. Okay, so yeah, the idea is that you have a goal, you perceive your environment, you reflect to see which action you want to make to optimize your goal, and then you need a way of actually manipulating the environment, right? So acting. So an agent is essentially that, right? It's this loop. You might have seen it very often. It's really perceiving, seeing what's in front of you, thinking about what's the next best action to do, and then actually rolling out this action in the world. So that's basically what's there is to agents, right? So insects are agents, babies are agents, you're also agents, self-driving cars are agents, AI that plays games like Go are agents, and same for StarCraft, same for ChatGPT. You'll see that a bit later. That's an agentic version of an LLM. So basically, all of these are agents. There's various embodiments of agents. It doesn't have to be a robot walking around in the world like you could imagine. So beyond the nice demos that I just showed you, there's something pretty interesting. There's a research group called Meter who are basically tracking the progress of AI agents across the years. And essentially, what this plot is showing is the length in human time of tasks that AI agents currently can solve and the extrapolation, basically. But they can solve at 50% success rate. This means if I give a task to an agent, 50% of the time it would complete it correctly. What they show actually is that the length of these tasks. Thank you. One second. Thank you very much. Cool. So what they show in the study is that the length of the tasks that AI agents can solve actually doubles every 7 months. Okay, this is pretty interesting. You can see this means basically that the length in your time, right, of the tasks that you can complete in software development that agents can solve is actually doubling every 7 months. If we extrapolate this way, it means that by 2027, AI agents could solve tasks that take 4 hours for humans to solve. This is what this plot is showing. And if this is true, it's actually quite impactful because 4 hours is roughly half of a workday for many people, right? So you can see how quickly we can move to agents that are capable of being quite impactful in the real world. I will actually get back to this. We have some experiments that we did to actually see if this holds for some types of agents, and I will show you some results a bit later. Cool. So before I tell you about LLM agents, I want to tell you about the classical way to train agents. So this would be before LLMs and foundation models, how would people actually train agents? So if some of you know about reinforcement learning, you guess that we're going to make a small detour in that direction. Okay, so typically, if you wanted to train an AI agent, what you would do, essentially, you would make it interact with an environment and collect some rewards, okay? So in reinforcement learning, the agent perceives a state, which is just an observation of the environment. It's able to make a limited set of actions, and then it receives a reward for its actions, okay? But the experimenter has to define the reward. That's actually quite tricky, okay? So it means that if you're trying to make a robot that will walk to some endpoint, you need to define a reward. That could be how close the robot has gotten to the endpoint over a course of a trial, right? And this, as we'll see a bit later, is quite hard for humans to define correctly. It requires some thought, and it can be, it's not infallible. There could be some significant failure modes to that. I'll give you an example very soon. But the idea is that once you have that, what you want to do is you want to optimize what we call a policy. And this is a decision function. So it's a function that's going to perceive a state and decide which action is the good action to make to optimize the goal. And actually, what does that mean? In practice, it means that we are optimizing what we call the expected discounted reward. So this is the sum over all future time steps of the reward that you expect to get if you're acting with this policy. So starting from the current state, if you start acting according to a fixed policy, what would be the expected reward you would get? And of course, we cannot sum up to infinity for this. So you use something called a discount factor, which could be between 0 and 1. If you set it to 0, it means you don't care about the future. You only care about the current step. If you set it to 1, it means that you care about all of the future rewards, right? So basically, you can play with that. And it really depends. It's up to the experimenter to determine what makes sense in their context. Cool. So giving you an example here, this is Albert. It's a robot. It's a small agent that's actually trying to walk. And the reward that's being used here is the proximity to the green square to which it gets. And you can see here, this is after 163 trials, 163 trials. And like, this is what I mean. You specify a reward, it's just get closer to the objective. It doesn't say walk like a human, right? So now you're starting from a neural network, which is the policy, that knows absolutely nothing. It's a randomly initialized neural network, right? And then it's trying to walk. So it can figure out whatever thing. You can be very surprised about what it learns. You can also, once you've made, this is 415 steps of learning, you can actually just get it to walk in more and more complex environments. And then speeding this up a lot, after almost 1,000 trials, you can see that it's kind of getting somewhere, right? It's skipping around the environment. Yeah, it's learning, right? This is an example of reinforcement learning in action, starting from a completely naive policy. And then at the end, when Albert is very expert, you can try to throw some blocks at him, try to make him fall. And as you can see, the policy is pretty robust. Okay. So this is just to explain to you basically what you can do with reinforcement learning and trying to optimize the reward. Cool. So there are two main paradigms in reinforcement learning. Michael and Noah have both talked about it. There is value learning and policy learning. We don't need to get into much details about these for the talk today, but I just wanted to contrast them and basically give you an overview. So value learning actually means that you're estimating this Q function, okay? We call it the value function. And essentially what it does is in the current state, if I make this action, what is the expected reward I would get, right? Expected discounted reward, which is the equation we saw before. So here you're kind of making the policy with an intermediate step. Your policy is going to be to select the action that maximizes this Q function. So that's one way to do it. It's been quite effective. This video you're seeing here is from a DeepMind paper. In the time it was called DeepMind Technologies. So it's from a while ago. It's a deep Q network. So it's a neural network that is estimating this Q function. And it's being used to play brick breaker. It learns this clever trick, you know, where you make the ball bounce on the top to break more blocks. So this has been found to work. There's been some successes. And then you can also use a more direct approach, which is called policy learning. And the idea here is to say, look, like, I don't want to take this intermediate step. I'm going to consider my policy to be a probability distribution on possible actions given a state, right? So you're trying to learn a neural network that will receive a state and that will say, okay, I think this action is more likely than the other in this given state. So you optimize things directly. So here is an example in the brick breaker case, right? So you would receive a state, you would pass that as input to a neural network. And then this neural network would say, okay, I think action one is more likely than the others in this case. And then you would not just pick action one, you would actually sample according to this probability distribution, which is nice because it gives you kind of exploration at the same time, right? You may sample, oops. Uh-oh. How much time do I have before it forces the update? 8 hours, okay. Okay. Oh, yeah. Bad timing. Okay. Nice. Okay. Yeah. So you're basically learning this probability distribution, right? And then basically you're learning to sample according to this policy. And what's nice here is that it actually supports continuous actions compared to the previous one that only supports discrete actions. So what's pretty cool here is that if A, for example, was a real value that controlled the speed of a motor, for example, you could actually learn that, right? You can learn some kind of continuous distribution over the value of the speed of the motor. This is a good fit for that, right? You could do it. So it has this nice advantage. And so a typical algorithm for that is reinforce. You've also seen another one in the previous lectures, which is GRPO. This is just another kind of policy gradients method. So essentially what the loss of reinforce looks like is just what you see here. So essentially when you minimize this loss, what it's doing is that you're increasing the probability of actions that have high reward. Okay, so you're just saying during the training, I really want to say, if I made an action and it led to a high reward, well, I want to remember that and put high probability on it next time, right, in similar states. So this is the loss we use in the reinforced algorithm. Great. So it's an extremely powerful framework. It's been used in pure reinforcement learning. I know Noah mentioned it didn't work really well yesterday, but this is more in the context of neural networks, right? So this was pre-LLMs, basically. Long time ago, right? AlphaGo, I think, was 2016, if I'm not mistaken, or 2017. But the idea that they use here is that they actually combine the two paradigms. They use value learning and policy learning, and policy gradients, sorry. So the idea is that you're playing the game of Go. There's many potential states in which the game can go. Your opponent can make other moves. So you're trying to estimate what is your best move given the best move of your opponent. And you can go like that for many tree depths, basically, to try to find the optimal decision to make here. And so what they would do at a high level is that they would use a tree search algorithm where you start from a state, which you see at the top, and then you would expand possible states given your policy, you would sample from your policy, basically. And then given all of these states, you would try to estimate the value, the expected cumulative reward that you could get. And essentially, this is a branch and bound algorithm, basically. So there's many, the search space is combinatorial. You're always expanding it based on your policy, and you're trying to estimate the value of a branch. And if the value is low, then you just say, okay, I'm going to stop. I'm going to focus on the highest value branch. And you continue. And you can do that forever, right? It's a classical algorithm from combinatorial optimization called branch and bound. So this is called MCTS when it's used in the context of reinforcement learning. Cool. So this is a really powerful paradigm. It's made some great successes, right? Like beating world champions at games. Nice. But it's also very imperfect. And I want to tell you about some limitations. If Zoom collaborates here. Yeah, great. So reward hacking. As I said, it's really hard for humans to define good rewards. Sorry, it's a bit laggy here, but essentially this is a game. This is a video from OpenAI. And the idea is that it's a boat racing game. And there's a course and you need to finish the race first to get the high score. And during the race, you can collect those green blocks and it gives you more points. And actually, if you optimize the policy on this game, you end up with something very surprising. And it's just that the agent figures out that it can go to some point on the map and just do circles and collect those green dots to maximize its score. And then the boat catches fire because it's crashing everywhere. But by the time it reaches the blocks, it kind of regenerates its health, right? So essentially what happened here is that you had this policy which you think was a good fit for your problem, but you were outsmarted by machine learning. So it turns out if you want to maximize reward in this case, you can just loop in circles. And this is not a useful policy, right? So this is one limitation, I would say, of the reinforcement paradigm if you're trying to train agent from scratch. Cool. So challenges in applying what I just presented in the real world includes, first of all, sample efficiency. So you saw that this is not really efficient, right? You saw the Albert robot that I showed you that was trying to walk. It took thousands of episodes, so we needed to train it for 1,000 times before it was actually kind of walking. So it's actually not that sample efficient, right? There's safety risks, right? If you want to make a robot for the real world, let's say you want to make a surgical robot, right? You don't want the robot to learn by trial and error on you. So there are some risks to doing exploration and like learning in the real world, right? So high stakes application, you can't just start from a randomly initialized policy and start acting until you get high rewards. That would be quite detrimental to society, I think. Reward design, as the boat example shows you, is pretty hard. You can think of good rewards, but it's very hard to think of all the edge cases. I'll give you an example later, actually, when we tried to do RL on LLM-based agents eventually, and it literally hacked our benchmark. So I will get back to that. And then generalization. One important aspect there is that if I take the policy that I learned for the Albert robot that was learning to walk in this simulated world, and I apply it in the real world, performance is not guaranteed to work well, right? It's a different distribution. The agent has not been trained in this environment. So you don't really have guarantees that it would generalize. So for that, people have been turning to foundation models, trying to learn better priors. And essentially, this is what we'll talk about now. So LLM-based agents, and here come foundation models, right? So the general idea of LLM agents is that you would take your agent, same setup as before. You have an agent, you have a world, you want the agent to act in the world, but instead of learning a policy from scratch, what you would do is basically put an LLM as the policy. Okay, at a very high level, this is what's going on. You take an LLM, use it as your policy, and this is an LLM agent. So in the rest of this part of the talk, what I will do is basically, I'll explain really what I mean by that. And we're going to see a hands-on example of this building actually agentic workflows using LLMs. So before I continue, are there any questions about what I just said? Good, okay. Anyway, stop me if there's questions. So what is nice about LLMs, right? Why would we even think of using an LLM as a policy? Like it's a text model, doesn't really make sense. Well, we know that LLMs are good at solving new problems zero shot, right? So when you take GPT and you say, okay, I want you to know how to multiply numbers, you can do a zero shot. When you tell it, if you explain it a new mathematical operator and you say, okay, give it a few examples, it will learn how to use it, right? So it's good at solving problems zero shot. As we saw yesterday with Nuha, LLMs are increasingly capable of advanced reasoning. They can use complex chain of thoughts to solve problems. And what's pretty nice is that you can communicate with them in natural language. So you could communicate the goals to agents in using text, right? You can write, your goal is to walk to this destination, and you don't have to specify this kind of clunky reward. You don't have to craft a mathematical function to be the reward in this case, right? So you can use your language to be able to communicate the goal to the LLM. So at a high level, this seems like it could be a powerful framework. But the main issue here is that LLMs are just stuck in a sandbox, right? So an LLM is a text generator. It has nothing to do with acting in the real world. So if I take, for example, GPT 4.1, and then this is from the OpenAI website, actually. And if I say, okay, what's the weather like in Yerevan today? And ask it. So let's do that. Do you think it will find it? No? Okay. So essentially what it does is it tells me if you want to see the weather, you can go to this and that website, okay? It doesn't really know how to do that. So what's happening here is that this is just a text generator. It doesn't have access to the external world. It doesn't have access to knowledge beyond its little training, but not little, huge training corpus, but it doesn't have access to updated information, right? It's stuck in this sandbox. So let's say I do the same thing and I ask ChatGPT, what's the weather like in Yerevan today? Well, let's see what happens. I'm sure you already tried things like that. So you can see it thinking, and then it gives us the weather. This was a while back, but you can see the weather. It's 26 degrees Celsius. I think it's hotter right now. But essentially it works. And why does that work? It's because ChatGPT is an agent. Okay, it's not just some LLM generating text. What you can see here is that if you open this little arrow, you will see that the model actually searched the web to find this information. Okay, so it made an action in the real world. And now in the rest of the presentation, we'll see how that actually works, how agents are able to go from text generation to actually acting in the real world to get information from their environment. Okay, so the first work that actually hinted in that direction and that was very impactful in my opinion is something called Toolformer. Okay, and the idea was very simple. It was just asking the LLM to output some kind of function calls in text, and then taking those, you parse them, you run them, and then you put the answer back into the model, right? So yeah, so you gave an LLM a set of functions. You say you have access to a question answering function, and you can use it if you need to search for some knowledge. So let's see. So out of 1,400 participants, 400 or, and then you run calculator, this thing, pass the test. And then if you see that in the output of the LLM, you would just parse it and you would replace that by the actual calculation that's been made. Like it's a super simple idea, right? And then all the LLM needs to do is output function calls in the appropriate format. So now we're going to try this. Okay, I made this. I made some notebook. In the practical session today, you will be able to play with it yourself. But now, essentially, what we'll do is that I will run it for you and then show you how this works. So, all right. Cool. Is this big enough for you to see the code? Is good? All right. Okay, so let's see this. I just want to install the packages. So I'm going to initialize an LLM client. Here we'll be using GPT 4o Mini actually. So let's just wait for this to run. Okay. So we're going to define a few tools. So I'm going to define this get weather function, which essentially, if you look at the code, is very simple. All it does is it takes a latitude and a longitude, and it will query some open weather API. Okay, and it will ask for the current forecast. Okay, there's nothing more to this. It's a simple get request to an API. Good. So, and it returns the current weather. And then I'll make another function that is a calculator. And this calculator, again, is very simple. All that it does is that it will receive an operator. This could be add, subtract, multiply, and so on. And it will receive two arguments, and it will just process them according to the operation that we require. Good. Okay, so there's nothing more. These are normal Python functions. Now I'll show you the basic way to do tool calling, okay? And you will get to play with that later. So I'm going to make this function. And if you're a professional of software development, you will think this is super sketchy. Like, don't try this at home. What I do essentially is I take whatever the LLM outputted between some square brackets, just like in the tool farmer paper. Okay, so this is what this regex is doing. It's matching those blocks. And then if it finds a tool call, what will be done is that it will execute it using exec. Okay, so if the LLM outputs like a sudo rm star, and I'm in trouble here. Okay, but thankfully this is a sandbox environment. Good, so we'll define that. And then we'll define a system prompt for our LLM. And you'll see here what we do is we say, okay, you're a helpful assistant, you have access to some tools to fulfill the user's request. And then I give it the doc strings of the functions. Okay, so I'm giving it the get weather function and then the calculator operation. And then I say, please respond with a tool call when appropriate and never try to infer the answer without calling the tools. And the reason for that is that this when you give a system prompt like that with tools, the LLM doesn't always use it, right? You kind of need to system prompt it into really using the tools, because otherwise, if you ask for the weather in Yerevan, maybe it will say, yeah, it's 29, and it doesn't really, it just hallucinates it, right? So here we're trying to go beyond hallucinations and actually taking signals from the real world. So good, let's define this. This will be the system prompt. And then we'll define a user prompt, which is, again, same example, what is the weather like in Yerevan? Okay, good. Then we'll make a call to GPT-4o Mini. So it says, to find the weather in Yerevan, I need its coordinates, right? Remember, my function accepts only latitude and longitude. So this is pretty cool. The LLM is using its background knowledge, whatever it has learned in its corpus, to make a proper tool call. So it's inferring the latitude and longitude based on its knowledge, right? So it says it's located approximately at those coordinates. I will now retrieve the current weather for Yerevan. And then it makes this tool call. Here it says, I want to call the get weather function with these arguments. Okay, so let's trust it and roll out, execute this function. Okay, I received this output from my API call. It gives me the time, the current temperature, and the wind speed. So now I give this back to the LLM. And as you can see, it tells me 29 degrees with a wind of 2.8 meters per second. So, or miles per second, I'm not sure. Anyway, so as you can see, this is GPT-4o Mini, which is just some normal LLM that doesn't have access to the external world, but now with these simple tool calls is actually able to get information from the real world. So this is quite powerful, actually. We can play with other kinds of prompts, right? So I can say, what is the weather like in the capital of Armenia? Need more background knowledge here, right? Let's try again. It says, the capital of Armenia is Yerevan. I will get the weather for Yerevan now. Please hold on. The coordinates are approximately this and that, right? So you can see it used again this background knowledge to infer the proper tool call, which I think is pretty cool. It shows the power of combining tools with actual background knowledge that's baked into these models. So let's go, let's roll this out. Good. Okay, so again, it works. Now back to the slides. So as you can see, this is pretty powerful, but it does have some pitfalls, right? So for example, LLMs, they're stochastic beasts, right? Like you don't really know, you don't have the certainty that they will listen to your system prompt. You can only hope for the best and try to craft the best prompt in this case. So sometimes the LLM could output, yeah, the answer is calculator 2 plus 5, okay? Actually, I did not show you this calculator example, so maybe we just do that before I continue. I'll show you this example. So I have 10 apples and I eat one. How many are left? Very difficult math problem for the model here. So it says, to calculate that, I need to subtract. I need to make this call, right? Subtract 10, 1. And then I actually roll it out. I will get 9. And then it says you have 9 apples left. Great. Well, that's a perfect example. Okay. So see what happened here, basically. It says no tool call found between brackets. This is exactly the point I want to make. Yes, most of the time the LLM follows what you ask it, but sometimes it doesn't, right? So now it outputted no tool call. Okay, maybe because it thought it was way too simple to do 10 minus 1, and it just did it out of memory. But this is dangerous for hallucinations. Or the model could just have outputted some incorrectly formatted tool call. It could have said calculator 2 plus 5, or calculator with arguments add to 5. Like, this is a bit of a stretch. But the idea is that it's a stochastic thing and you don't really know what it will output, right? So people have been working on something called structured outputs. This has been really impactful for agents. Essentially, what you do is models have been increasingly trained to output JSON in some very specific formats, which means that you can tell the model, look, I expect you to output this exact format in the output. And usually this will really reduce parsing errors, right? Or basically make it more reliable if we can standardize the outputs that we expect. And there's some great Python packages like Pydantic that really allow you to do that. We'll get to play a lot with Pydantic in the practical session. But essentially, the idea is that you could specify an object in Python. You can specify a class. And then Pydantic will use a context-free grammar to guide the decoding of the LLM, which means that it will not let it generate any kind of output at once, and then hopefully you parse the tool call. It will really guide step by step the decoding in the proper format. Good. You can also use regular expressions. People have been doing that. Great. So let's try this again. As you'll see, like most of the slides now will be like, okay, this is something, let's try it. So we're going to go and work on what I call improved tool calling. So here, what we'll see is exactly the same example. We're going to define, I'm going to show you actually, this is the format that is used by most modern APIs now. So you define your tools, which are functions. You define them as JSON. You make a description of them. So you'll say, this is a function. It's called getWeather. Here's a description. So the LLM will use the description to select the functions it wants to use. And then you specify all the parameters. You say there is latitude, it's a number. Here's a description. There's longitude, it's a number. So if the LLM wants to output some string for that, it's just not going to work, right? It's going to make sure it's actually a number. And you tell it which arguments are required. Okay, so you can see that this is guiding the LLM way more than just asking it to generate whatever syntax and hoping for the best. Okay, so let's try again. What's the weather like in Yerevan? And what we'll do is we're going to give the tools to the API here. So this is the LLM API. It's the normal ChatGPT API. And I'm going to use 4.1 nano for that. So I give it the tools, and then I'm going to extract basically a tool call from it. So you can parse whatever you get from the LLM API. If it contains a tool call, you're able to extract the function name and the arguments from it. And then I'm just going to apply it. Okay, so this is what I do here. I'm going to go get the function from memory and just apply it with the arguments. Cool. Let's try it. Great. So now you see we have something a bit more structured. The LLM is saying, I want to call the getWeather function with arguments, which are the following. And as you see, these are not strings, right? These are the floating point numbers. So nice. So the parsing has worked. And now what we'll do is we'll give this information to the LLM. And again, we get the same answer. It's 29.4 with winds of 2.8 kilometers per hour. Great. And if we want to go even further in controlling the generation here, we can use Pydantic. This is what I was telling you about. You define a class that you call weather. And you say it has two variables. It has temperature, which is a floating point number, and wind speed. And then you actually give to the LLM API, you give it an expected text format. And this is just the class that you just defined. What's really cool with that is that you will actually get a Python object, right? So this thing, like you get all the parsing directly. So you prompt the LLM with text, and then you can get Python objects. Okay, and the rest of the presentation will just be about leveraging the power of this little kind of setup, right? As you'll see in what's coming, we're going to build a pretty complex meeting summarization workflow, and it will be based on this very simple idea. Cool. So, all right, little break from the practical session here, just to show you the possibilities of what can be done. Basically, what can be a tool, right? So tools can be databases. You can use a database as a memory or a knowledge graph as a memory to say, I want to remember the name of the user. So whenever the user says, hey, my name is Alex, you would actually make a function call that would save the name to the memory. Or if you learn preferences of the user, you could save them to a memory. You may be able to use productivity tools like using Word or Excel. We'll see examples of that in the practical applications part of the presentation. You could use search engines. So if you use ChatGPT, sometimes you see searching the web. Essentially, it's calling an API that allows it to do to get search results from the internet. You can use a computer as a tool, right? We've been doing that at ServiceNow. You'll see an example soon. You can use maps, code, whatever, right? So essentially, if you want to push this to the extreme, you could even interact with the real world by using robots, like basically robot arm as a tool, right? And then your function calls are setting the parameters of this robot arm to act in the real world. So like this is a pretty powerful framework. It's just basically parsing the outputs of an LLM and converting it into actions, but it's a really powerful framework. Great. So I don't know if some of you have heard of MCP. Anyone familiar with MCP here? Nice. Okay. Good. Yeah. So MCP is being pitched right now as the USB-C of agents. Okay. And the idea is that it was introduced by Anthropic actually. So you can make an MCP server which exposes a set of tools. Okay. And so, for example, here you have a server that is exposing internet. So this is probably like web search. You have GitHub. You have Slack. Okay. And then the MCP server is an abstraction layer that the LLMs can interact with. So I make an MCP server for whatever I want. The LLM sees a standardized format, which is based on JSON again. And then basically MCP client is something to which you can give a number of MCP servers. It will discover all available tools and it will give them to the LLM. Okay. So in the practical session later this afternoon, you will actually be building an MCP client, a chatbot with an MCP client that's able to interact with arbitrary tools. And what's really powerful about this framework is that it's kind of like plug and play. If you respect this format, anyone can make an MCP server for anything, and then anyone can just install it, and their agent is immediately able to use it, right? So this is really the power. It's kind of this plug and play framework for tools in LLM agents. So yeah, you will get to play with that pretty soon. Cool. Oh yeah, there's actually search engine now for MCP servers. So if you're interested in building in what we'll see this afternoon, there's actually like here you see there's 15,800 such MCP servers. Like there's been a crazy ton of MCP servers proposed. So the idea here is really like you want to use, I don't know, Microsoft Word with your agent. Check on the search engine for MCP. There's most likely an MCP server for Microsoft Word. And then basically out of the box, your agent, if it can be smart enough to use it correctly, would be able to interact with Microsoft Word. Great. So this is why it's called the USB-C of agents, by the way. Cool. So the fundamental building block of what we'll see next is what Anthropic calls the augmented LLM. It's essentially a normal LLM. It's basically what we just did, right? So it's an LLM that receives an input that is able to make one or more tool calls and then produce an output. Okay, so this basic building block, and you can, in this, this was a blog post by Anthropic, but essentially what it showed is that you can combine these building blocks to build arbitrary complex systems, right? So yeah, so let's give you an example. Any questions, by the way? No? Yes, question. Yeah. That's correct. So the reason why I'm using GPT here, OpenAI models, and not like Llama, for example, is that technically it can do it, but smaller open source LLMs are generally not that great at calling those tools. So you need a pretty good model to be able to call the right tool in the right context. So what you're mentioning is probably companies are saying, look, I don't want to use this huge model to make my agent because it's too expensive. So I will kind of fine tune a smaller one, but with my function and my use cases so that it's better at calling the right tools in your own context. I'll get back to that, but essentially that. You're welcome. Any more questions? All right. Okay. So, all right, then let's move on. We have plenty of time, so don't hesitate to ask any question you have. Okay, so agents, right? There's various levels of autonomy in agentic systems. As I said, they're all built on this simple building block that we just saw, the augmented LLM. This will be really what we use as the basic block in the rest of the talk. So I'm going to talk to you about two kinds of agentic systems. There's workflow and there's like fully autonomous agents. Okay, but the reality is that you really don't need a fully autonomous agent for most practical use cases. In fact, it could be quite dangerous to just say like, look, here are functions, do what you want. This is the goal. Okay, so often what people do is that they build something called workflow, which is kind of combining LLMs that are using tools autonomously, but with some logic that you hard code. Okay, so actually made this picture with ChatGPT, but that's why there's typos. But basically, you can have an LLM call that fits into this greater logic that you have implemented, and then you can chain basically normal code with LLM calls. So basically, you keep full control over the execution path. You just have little blocks in there that are LLMs that are actually doing some processing. This will get more concrete in the practical example in the next slide. But the idea is like you have more control, so it's easier to align with business logic. So, for example, if I'm making a customer support kind of agentic system, and then it receives an email, and I want to know which department to route it to. Okay, I could ask the LLM, okay, look at this email. You have three choices where you want to send it, and then I would manually send it to this department. So that would be an example of a workflow, right? The LLM is making one decision point, and then I'm doing the rest of the execution. So that's an example. It's less flexible, but you keep more control. It's essentially, if you think about the RL stuff we just talked about, this is like a hard-coded policy. Okay, so it says, now that you've received this, the execution flow is going to move in that direction, and the agent doesn't have control on that. This is the coder who has access to that, right? And then you have another kind of agentic system, which is agents, like fully autonomous agents. And essentially, you just give a bunch of tools to an LLM, you give the goal, and you say, okay, please use the tools to solve the goal. This is very flexible, right? So I can, as we'll see soon, I can give you access to a mouse, keyboard, and pictures of a screen. And I could say, okay, like write a document for me in Microsoft Word. And the agent would probably be able to do something, but you don't really have a guarantee that it would be anything robust or that it would be high quality. So the idea here is that these are called agentic systems, and there are various levels of autonomy in agentic systems. Workflows are the least autonomous, but you exert more control on them, and then agents are fully autonomous, and they're very powerful, but quite hard to control. Cool. So in the rest of this part of the talk, we're going to build this system together in the Colab notebook I was using. Essentially, this is a system that will receive a transcript from a meeting, and then it will summarize it in the format that is mentioned by the participants of the meeting. So we'll see someone say, okay, I'll send you a slide deck to summarize the meeting. And then the agent will actually pick this up, make a slide deck, and we'll translate it in the language of each user. Okay, so we'll build this thing that is quite fancy, and you'll see it's not that hard to do if we use the augmented LLM building blocks. So, and while we're doing that, I will tell you about common design patterns that you can use with LLMs. Again, this is all taken from the Anthropic blog post on building agentic systems. So I'll show you basically cool tricks that you could do with LLMs. So this is what we call design patterns here. And then we'll be able to combine all of those together to make complex agentic systems. So we're going to start with the first one, which is called prompt chaining. I'll go back to my computer to show that to you. Okay, so by the way, don't hesitate to stop me at any point if ever you have questions. This will just be more interactive. Cool. So basically, prompt chaining, what it does, actually, what we'll do here is that we'll make a first LLM call. Again, when I say LLM call, I'm thinking augmented LLM, okay? This is an abstraction. So this is an LLM that's allowed to call one tool. So it gets an input. We're going to make an LLM call, and then we're going to have a logical decision that is hard-coded by us. And then maybe we'll make more LLM calls to eventually reach a terminal state. Okay? Super simple. Let's try it together. So again, we're going to make a meeting summarization system here. So we'll first start by defining the augmented LLM, which is our fundamental building block. It's going to be some function that receives a prompt, receives a list of tools, and an expected format. Again, Pydantic, right? This is what we just saw. And then what it will do is that it will actually roll out any tool call in the output of the LLM, and it will just parse the output in the expected format with the response format. Like there's not much to this. It's really just a list of tools in an expected format, and then you let it go. So I'll just run this. Okay. Now we're going to define a set of functions that we'll use throughout this building the system. As I said, you need to define them in JSON again, so the LLM understands which functions it has access to. So I won't show you all of them, but these are functions we'll be using over the course of this part. Again, they're all specified in JSON. You can take a random one like translate slide deck, and you can see it translates a slide deck to different languages and returns a path to the new deck. Basically, it has two arguments, the path to the initial slide deck and the expected output language. Again, nothing more than what we did in the previous one with the weather. Cool. The data we'll be using, as I said, like this is a meeting summarization system. So we'll assume we start from a transcript. Maybe Zoom produces this transcript at the end of the meeting. This is actually a meeting about some kind of strategic project called Project Arcadia. This was GPT generated just to have some transcript between people. And then you have a list of people participating in this meeting with their emails. And then you have everything they said throughout the meeting, okay? So yeah, I can send that by the end of the week. Great, let's talk scope, blah, blah, blah. They're basically defining a project. And you'll see at the end of this meeting, Alex says, thanks, let's regroup in a week to review the first draft. I'll send you a slide deck to summarize our discussion. Ooh. This is the cue for the LLM to produce a slide deck, okay? Let's see how this works. And then separately, we'll define user preferences. So we'll say, okay, Alex will speak in English, and Jamie will speak in Armenian. Okay, but beware, like GPT is not that great. Maybe some of you are aware. I showed the slide deck to Peruz, and she told me, "Well, this is not great." so, so let's see. Let's see what happens. So prompt chaining again is the first thing we'll do. What we'll be doing here is that we'll be taking a meeting transcript. We'll be loading the participant information. So from this transcript, we'll be extracting the participant information. We'll be checking if participants are authorized to use this tool. If there's an unauthorized participant, we'll abort. If they are, we will continue and extract the expected summary format. Okay? So first function, load the meeting transcript. It's a bit of a dummy function, just returns the variable we defined. And then check unauthorized attendees. This is the interesting one. So you should pay attention to this one. Basically, all it does is that it receives the meeting ID such that it could retrieve the transcript, and it retrieves a list of authorized domains. And then we're going to ask the LLM to output this thing. So basically, it checks if there are unauthorized attendees, and it's going to output yes, no explanation. This is just some class that I made. It expects a Boolean value that says, are there unauthorized users or not? And then an explanation for it. Okay, so usually you would have to write code for this. But here, all that we'll do is we'll make a prompt that says, does meeting ID have attendees from unauthorized domains? Here are the authorized domains. Okay, and then I'll give it access to a tool that is loading the transcript and say, I want you to output a yes, no explanation. Okay, so technically you could have written code for that. You could have extracted the emails and then just kind of did your own logic. What I want to show you here is that you can basically do some pretty powerful operations without having to write code for it, right? So then after this function, we'll be using something called get expected summary format. And the idea here is we'll say you have two choices. Okay, again, this is Pydantic. We'll say the summary format is either slides or PDF, you choose. And then the prompt will be, what is the expected summary format for the meeting? Look for an answer in the transcript. If nothing was discussed, fall back to PDF. Okay, so essentially, people could have said, I will now send you a slide deck. Or they could have said, can you send me a PowerPoint? Okay, and then, or can you send me a Google Slides? And then the LLM with its background knowledge could infer that people expect to receive slides without you having to code anything. So you can see that this is giving you a lot of flexibility. You can use the common sense of the LLM to do something that you would usually have needed to code. But again, I would advise you to um, write a lot of good unit tests if you're going to do something like that, because like you really need to design this prompt such that it's reliable. It's stochastic, right? It's an agent. So maybe even this one, maybe sometimes it will tell us 9 times out of 10, it will say, yeah, it's slides that was discussed, but sometimes it will say PDF. So you shouldn't be using things like that for critical, like very critical business processes, for example, okay? So now companies are talking all about using agents everywhere, right? So um, let's say you're building a customer support agent and then it has to emit reimbursements. Well, if like 6 times out of 10 it emits reimbursements it was not supposed to, you're losing money, right? So you should be careful. Maybe it's 9 out of 10 and you say, okay, I accept this loss because I don't need to write fancy code and it's enough. But there's kind of a trade-off between reliability of these things and the effort that goes into building them. But it brings a nice paradigm where you can do like before, like even now, people were talking about test-driven development, right? You would write unit tests, you would write code basically, and then you would check if the unit tests pass. If they pass, you would say, okay, good, the code is nice. So if you have a solid set of unit tests, now instead of writing code, you could basically write some text and say, look, you need to do that and craft your prompt until it's reliable. All right, let's see this in action. So the meeting ID is ABC123. The authorized domains is just northloop.com. External.com is not allowed. So technically, if you remember the transcript, there was one participant from external.com. Would expect the LLM to reject, right? So what's going to happen here is that we're going to check for unauthorized attendees, and we're going to use the output. So if has unauthorized dot answer. If you remember, this was the Boolean value. And then I'm going to raise an exception with the explanation that the LLM provided. So let's see. It worked. Okay, so it says, cannot proceed. There's external users. The meeting attendees are Alex at northloop.com, Jamie at northloop.com, and Taylor at external.com. The authorized domain is Northloop. Taylor's email is external, which is unauthorized. Okay? So you can see basically the reasoning that went behind this, and the LLM decided to reject, saying that there was unauthorized users. Good, so it seems to work, but in fact, I had to optimize this prompt quite a bit to get it to work reliably. I don't want to hide that. So let's run it again. Now what I did is I authorized all the users by just uncommenting that. And boom, you see it ran, and it got to this point where it said, give me the expected summary format. And it's looked at the transcript. You see a tool call, like tool call looking at the transcript. And the summary format it decided is slides because this is what was discussed. Cool. So this seems to work. Now, enough with prompt chaining and moving back to a new design pattern that is called routing. So essentially what you could do is you can get an LLM to decide between various branches in the execution flow. So, you know, like this is kind of not a new design pattern, right? People have been building what they call business workflows for a very long time, right? So they said, okay, if you want to buy whatever for the company, you want to buy a new printer. Is the amount above some value? Yes. Okay, it needs to go to the vice president. Is it above this other value? It needs to go to the president, right? So like this is just basically normal workflow, but you're using the LLM to decide where you send the execution. So let's try this together. What we're going to do in the case of our meeting transcription workflow is that we're going to continue basically building. So we were at this point now, right? So we had the expected output format. Now we're going to route to the appropriate kind of summary. Okay, so we could have, for example, producing a slide deck. We can have producing a PDF summary or bullet points. And this will basically branch across the three types. So what I'll do, first of all, okay, so let's actually see the first function. I'm going to make some pretty complicated pydantic structure here. So I'll define what is called a slide deck. It's basically going to be a list of slides. And a slide is going to have a title and a content. So like pretty simple, but this, like, I find that pretty impressive that LLMs are able to generate these kind of complex structures. You'll see it in action in a few seconds. But essentially, what we'll have now, sorry, slide deck to PPTX. This is just a helper function that will take a slide deck object produced by the LLM and save it into a PowerPoint file. So nothing very fancy here. And then this is another function just to load one. So don't need to pay attention to that. This is the important function. So generate summary slides. Again, it's going to receive a meeting ID. And basically what it's going to do, it's going to tell the LLM to say, generate a slide deck with multiple slides to summarize this meeting. Use emojis to make it nice. Okay, so I added that for the visual features. And then it has access to a tool, which is just loading the transcript. And then it expects the output to be in a slide deck format. That's it. And then I call the function to save it to a PowerPoint. So let's see. Honestly, I didn't want to code this function, generate PDF summary, because we're going to be using slides in the example. So there's nothing there. It should just not call that. And then we have a big generate summary function that will say, okay, generate a summary for the meeting and return the path. Here's the expected format, basically. So just summary type. And then I'm going to really let it choose between two tools. It's going to have the option to choose between generate summary slides or generate summary PDF. Okay, so I'm not telling the LLM which one to choose. It's going to choose automatically based on its reasoning. So let's define that. And then first of all, I want to show you the generate summary slides function in action. So what it's doing now, it's looking at the transcript. See, it made a tool call to load the transcript, and then it produced a slide deck. So you see, again, this is the Pydantic structure, right? So the slides are a list. The slide deck is a list of slides. Slides have a title, Project Arcadia Kickoff, and then it has content. And you can see the content here, and you can see you have many slides. This is just a very big slide deck. Great. So now let's put that again in action. What it's going to do is going to look at all users to see if they're authorized. It's going to determine that it needs to build slides. It's going to produce the slides, and then we'll look at them together to see if they make sense or not. Great. So it produced this slide deck called Meeting ABC123. Okay. So let's look at it together, actually. I will download it now. Did this work? Did not work. Okay. Yeah, let's go. So switching presentation now to the summary of the meeting Project Arcadia. Okay, you can see it's not perfect. I would need to refine this a little bit because it kind of outputs 2 bullets for each line. This is a common mistake. I don't know why it does that. But anyway, it's a summary of the meeting. Basically, what I think you need to take away from this is that like there's not much code, right? It's just writing text to some building block to say and giving it an expected output format. So you can see like this is avoid crypto vibes. This is quite powerful as a tool already. Good. So let me just close this one and go back to my presentation. Cool. So this was routing. Okay. Essentially, we learned to dispatch the execution flow to different branches based on the LLM's reasoning. Here, it extracted that it should make a slide deck and decided to send the execution there. Another design pattern, which Nuha has talked about a little bit, like in the context of generating outputs, you can have a self-critique and basically learn to refine it. This is the same, but applied to agents, okay? We're going to make 2 LLM blocks. One is going to generate some slides. The other one is going to be a judge that looks at the slides and says, no, this is not good. And then reprompt it with some feedback until basically the slides are of sufficient quality. So what you'll see here is essentially that. It's called an evaluator and an optimizer kind of loop. There's an output, there is feedback, and then once it's accepted, we'll move on with the execution. So going back to there, I'll close that for now. So again, we were at this point, we produced a summary slide deck, but now is it good enough? Probably not. So what you could do is you can get the output file, this red circle, you can give feedback and ask for revisions until it's deemed of sufficient quality, and then just recall this function and loop until the better summary file has been produced, right? So let's see that. Let's see how to build it, actually. So I'm going to make a class. Again, it's always the same thing. I'm going to make a Pydantic class called feedback. It's going to have a feedback string. It's going to have an acceptable quality variable. And essentially, this is going to tell me if the slides are of sufficient quality. And then this function, evaluate slide deck, will take a slide deck and a meeting ID as input. And And then the prompt is quite complicated. I had to play a lot with this one, which is why you see there's much more text here. So it says, decide if the summary contains in the slides of suitable quality. Key points of the meeting should be reflected. The last slide should be action items. The slide should not use markdown text because actually this is what was leading to the double bullet points, and should not be overpacked. Give feedback, blah, blah, blah. Okay, so it's giving feedback here. And then it has access to a tool to load the transcript, and it should output feedback. Now I'm changing the generate summary slides function to have this loop. So we're going to make 5 attempts to refining the slide deck. So again, I'm going to call an augmented LLM with the same function to call the slide to build a slide deck. And then I'll allow it to basically, the slides will get reviewed by the evaluator. So review equals evaluate slide deck. And then if they're acceptable quality, I will move on. If they're not, I will append the feedback I received to my current feedback and try again. And I'll do that 5 times. And then basically what I did here, just to be a bit more fancy, if ever GPT-4o mini fails 4 times, then you switch to GPT 4.1 mini. Okay, so it's just trying to say, I'm going to try to avoid paying a lot for this thing. And then if ever I really need to, I will pay more. Okay, so you can see how you can kind of like adapt the execution to reduce cost and only use more costly models if ever you need to. Okay, so let's run this. Again, exactly the same. We're just building on the current workflow. So it's producing summary slides. It's making a tool called to load the transcript to check if the slides are actually faithful to it. Then hopefully it will fail on the first shot. Let's see. We found the slides were good enough already. Let's run it again. In the practical session, you'll be using open source models, and these tend to produce like lesser quality outputs. And you will most likely see this loop saying, nope, this is not good. Nope, this is not good. And it will iterate, like often it does, like, this is too good. Often it takes like 2 or 3 times, and then eventually it makes something decent. So like in the interest of time, I think I will just skip. Maybe let's try one last time. Just so that you can see it in action. Otherwise, you'll see it in the afternoon. Oh, there is a significant lag with the team. Okay. Let's see. Okay, it's just too good. Whatever. So these are, I won't show you again the slide deck yet because this is essentially the same as what you just saw. So that's a common design pattern. Another one is parallelization. So you can actually get the LLM to output multiple tool calls and then roll them out in parallel and then basically aggregate the output. So it's a bit like a MapReduce kind of pattern here. And then another one you can do is you can get the LLM to make multiple calls in parallel. So you could say, look, the one we're going to use as an example is saying there are 3 users in this meeting. You want to send the summary to all 3 users. So the LLM will in parallel start the workflow to send it to each user. Basically, so that's an example of this design pattern. Let's see it in action again. So again, what I said is that now we are at this point, we have what we call better summary file. Just waiting for the projector to catch up. Okay. So what we'll do is we'll extract the list of attendees and their expected languages. We'll translate it to their expected languages and we'll send them by email. Good. So that's it. So I'll make this function called get participant emails, and it will output a mailing list, which is just a list of emails. Again, Pydantic and a prompt. I said get the emails of all participants in the meeting. It loads a transcript, and then it just returns dot emails of this thing. And then the send email function is a dummy function that I made. It just pretends to send an email. And then translate slide deck is like, I think it's pretty powerful. So what it does, it takes a slide path as input and a language, and it will prompt the LLM to say, basically just translate the slide deck to an arbitrary language. You can do whatever language you want. Of course, the quality will depend based on the language. And so once it has been translated, you save it and then you return the path. Nothing more fancy than that. And then the orchestration happens here. So you tell the LLM, send an email. Oh, sorry, that's sent to user. So again, I'll skip over this. This is just like literally sending the email to the user. It has access to one function that is send email. Nothing fancy here. But then this one is where the orchestration happens. It receives a path to the summary, a list of emails, and it says send an individual copy of the meeting to everyone in the list of emails. And here are the slides. So here the LLM is expected to autonomously determine that, oh, I need to send it to these 3 people. You don't have to code the logic for it. You don't have to code the loop or whatever. This is just done by the LLM itself. So we're going to do that. And then let's try it. So again, it's going to get the participant emails. There's 3. It's going to call send to user 3 times. Now, just because I wanted this to be readable, I did not do it in parallel, but I could have executed those in parallel. Essentially, the LLM outputs 3 tool calls. So what it does, again, like for Alex, the language is English, so it will not do anything. Oh, it crashed. Interesting. This is interesting. So even then, it's not fully reliable, right? I think this is not the syntax error. I think this is just a failure of the model. But let's rerun it just to be sure. So Alex's summary is in English. That's expected. Now translating slides to Armenian is what's going on for Jamie, because Jamie's language is Armenian. There you go. Okay, I cannot judge if it's good or bad, but let's look together. Maybe you will laugh very hard. Let's see. Does this make any sense at all? So this is GPT's version of the meeting in Armenian for Project Arcadia. As you can see, look, like it's not, some people are laughing. Okay, it's making bullet points, right? It's not doing the 2 bullet point thing again, because we kind of have this refinement now. It's using kind of emojis. It used markdown there. It failed. It's not perfect. Does this make any sense? It's really bad. Can you raise your hand for this is terrible? Okay. Good. So, all right. This is the Armenian version of the meeting according to the GPT, and I guess this is takeaways because of the bye-bye sign. Yes, question. Oh, sorry, the microphone. Thanks a lot.
In agentic environments, when you have complex tasks and it involves numerous LLM calls, how you preserve memory? Because if you just append with tokens, it will eventually exceeds the token size, right?
Yeah.
So how you preserve the memory?
That's a really good question. So right now, there's prompt engineering, and now people are talking about context engineering, because essentially that's the main limitation. This is an easy task. It's not very long, the context, so you never reach the limit. But when you do like computer use agents, your observations are massive. You'll see it in the next slide, sometimes hundreds of thousands of tokens. So, and if you want to keep like 3 steps back, you need to keep 300,000 tokens in a prompt. So what people will do is they will use like summarizers. So they will basically look at the past steps and ask another LLM, look, summarize what was done for me. And then it will say, okay, you did this, you did that, you did that. The essential information was this and that. And like you basically, it's really context engineering, and you can use various tricks for that. Thank you. You're welcome. Question in the back.
Yeah, thank you very much. I have a question related to that part when you check authorization, like delegating it to LLM, and then also at the end when kind of deciding to whom send, like the participant list, also kind of delegated to LLM. Do you think that it will be the common pattern to delegate to LLM things like that, or is just for demo purpose, and in reality it should be done like separately in more reliable way?
Yeah, that's a really good question. And yeah, I have strong opinions about that. I think what you can code reliably should never delegate to an LLM. This is really for demo purposes. unless maybe you are prototyping, or maybe you're making a product for people to write like low code workflows, for example. This is a thing, right? Coding some logic without having to write code. Yes, it kind of makes sense. But if you have someone who knows how to program and you can code a simple function for it, like extracting the list of emails, like don't use an LLM for that. It's really just for demo purposes. And why you would not use an LLM for that? First argument is robustness, but there's also security issues that we'll see soon. Good question.
Hello. Quick question. Earlier we were talking about like there's tool calling data sets that are used for SFT and as well as like planning for a workflow. It's just kind of maybe like a research question, like a speculation, but you can picture if you were doing like MOE, mixture of experts.
Yeah.
Could you make one of the experts just really good at handling structured outputs and doing tool calling? Would that make sense? Is there any like literature on that?
I'm not an expert of mixture of experts models, but I think it does make sense. Or like you could, LoRa adapters for models. You could like make an adapter that is very, very good at using tools in one given context, and you would activate it in one context, basically. And so yes, the answer is yes, I think that would be possible. All right. Okay, great. So I will move. Oh, I think there might be a question online, actually. I have a general question. How we can assess model accuracy, which methods? Yes, that's a great question. Yeah, so what I would say, how to assess reliability or accuracy here, like in this context, specific context, I think that would be write unit tests, right? So like write the expected input and output for some examples, and then make sure that at least your agentic call is scoring very high on those unit tests, or like solving them at least like maybe 100% of the time. If you don't care about getting perfect reliability, maybe 90% of the time or 99%, depending on the criticalness of whatever you're trying to automate, right? So maybe it doesn't matter if you receive a PDF instead of slides 1 time out of 10. But if you make a reimbursement for $1,000, then you kind of care, right? So it really depends on the context. Yes.
Is it good approach to use LLM as a judge to evaluate the accuracy of the LLM?
That's a very good question. I will get back to it later in the presentation. Short answer is not really. Okay. Cool. So again, like what I said is that, again, we started from the augmented LLM, which is a small building block, and we're able to make a pretty complex system out of it, right? So you see that this is a pretty powerful framework. But then let's say we want to give full autonomy to an agent, right? And only just let it act, given a set of tools, and decide when it wants to stop. Let's try this together and see what happens. Okay, let's continue here. So what we will do now is essentially I define a new tool that is task completed. So the agent is allowed to call that whenever it has finished its task, and we'll just stop the execution. And I'll ask it to output a summary of its work. Okay, so, and we'll just print it and say bye. So the agent here again is going to be a loop for a maximum number of steps that receives a list of tools, and that will literally just call the tools as much as it wants until it thinks it has completed the task. Okay, so I'm not doing any kind of fancy workflow here. This is essentially what's going on. It gets a prompt, summarize the meeting, and send it to all attendees in their respective languages. If some users are from unauthorized domains, refuse to continue, deduce the preferred summary format from the transcript. Here are the user preference and the authorized domains. Go. Okay, and it receives all the tools. So let's see how this works. Oops, I did not define the function. I think I will have like 10 more minutes on this part, and then we can have a short break before we continue. Cool. So now you'll see it like first it loaded the transcript. It needs to understand what it's looking at. Now it's generating summary slides. Oh, slides of insufficient quality were produced. Don't forget to include all key points from the meeting in the slides. to ensure comprehensive coverage, ensure that the last slide clearly lists all action items. So it's giving feedback because the slides were pretty bad. And then eventually it made slides of sufficient quality. So it's continuing, translating the slide deck to a bunch of languages. Probably, honestly, I don't know why it translated it twice, because there was only Armenian in the list, but the default was English anyway. Maybe it translated it to English. So now it's messaging Alex saying, here is the meeting summary in English. It's messaging Jamie to say, here's the meeting summary in Armenian. And it's messaging Taylor with the default language because we don't have preferences for him in English again. And then it says, I've completed my task. I loaded the meeting transcript, verified all attendees were from authorized domains, determined that the slide deck is a preferred summary format, generated a slide deck, blah, 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 blah. And then it says, completed task successfully. Okay, so we had nothing to code here. It's just, I give you a set of tools and I say, okay, do it, right? So you can see here it worked, but it can go really bad, right? Like we can actually, yeah. So this can be pretty wild. What can happen? I'll get back to that. Let's continue for now. Okay. So this was full autonomy. Now this was the most general form of agentic pattern that you can build. In practice, like there was a question about should you be doing that? My answer would be if there's a specific logic that you can code, don't use a fully autonomous agent for that. Just code the logic. It will be way more reliable. But if you want to make a very flexible system that can do many things with a set of tools, then yes, it makes sense to use an agent. We will see some real world examples of fully autonomous agents pretty soon. Now, just before I continue, I wanted to say that some people have been looking at adding reasoning. So reasoning is a thing you saw a lot yesterday, right, with Nuha. The idea is that instead of just telling it, here's the input, give me the action, you could let it output a bit of reasoning before selecting the action. This has been shown to help. So there's this paradigm called REACT. It's reason and act. So the idea is quite simple. All you would do is say, you would let it think. So thought number one, I need to search Apple Remote and find the program it was originally designed to interact with. Okay, action, search Apple Remote. Okay, so you let it think a little bit before outputting. It's essentially that. And then, so we can try it here. What I'll do now is say, I just added a step and said, now reason about what you need to do next, okay, to the agent. So we'll run it together now. Same agentic setup. It's just now it's going to think before it does. It's not really thinking, right? It's outputting some chain of thought and then conditioning on that to decide which action to make. In practice, this has been shown to improve performance. So I need to load the transcript of meeting ABC123 to deduce the preferred summary format. Then I will check the list of attendees to verify if they're authorized domains and so on. So this is like the thoughts that the agent had, thoughts before making the action. And like in the interest of time, I will let it go in the background, but essentially it's thinking, saying all email domains in a transcript are authorized. The user preference indicate that Alex prefers English and Jamie prefers Armenian, and so on, right? So it's basically just adding some reflection before doing things. Cool. So to recap what we've seen, okay? We've seen that an LLM agentic setup essentially involves an action component. So here the action was selecting a set of tools and an environment, right? Here the environment was it's a bit abstract what it was. It will be more, the environments will be more clear cut in the coming parts, like we'll be using computers as an environment and so on. In addition to having access to tools, the LLM can have access to memories, okay? As I said, someone asked a question about how do you fit things in the context if it's executing for a long time. What people do sometimes is they make memories. This could be like SQL database. And then the agent could retrieve from this database based on the context, could retrieve whatever it remembers what was useful. Some agents involve a planning component, like the reasoning and acting that we just saw in the previous slide. So that's an example. There's many other paradigms like self-critique, chain of thought. Like chain of thought is the closest to what we just saw. You can use tools like web search calculators and so on. And then you can even have a memory where you can store new tools. And then just to finish, I want to show you this really cool agent. It's called Voyager, and it learns to play in simulated worlds this is an example where the agent was learning to play Minecraft, and actually it could write some. It was playing the game, and when it found that it did something useful, it could write a snippet of code to remember this action and store it into a long-term memory. And whenever it wanted to use it again in the future, it could just pick out this tool that it created for itself and roll it out. So what they showed in this paper is that this significantly improved the performance of the agent, and it actually makes things a lot more reliable too, right? Because now, once you've written a tool, it's deterministic. It's a piece of code. You can load it and run it. It will always give you the same output for the same input. So this paper was about creating tools for itself, and I think this is a really nice idea. It's been picked up now in a number of different contexts. And so I started by talking about RL, and then we talked about LLMs as policy, but this is all zero shot. Like there's no training involved, right? So should we forget about RL? Like it's not needed anymore? Well, obviously not. Given what you've seen in the previous presentations, RL is being used increasingly for LLMs. And later in the presentation, I'll show you how it can be used to improve agents. So that's it. I think we're at 10:30, so maybe it's a good time for a short break. And then we'll continue with real-world applications of agents.
Everyone, we are planning to start in few minutes. Take your places, please.
All right. All right. Let's start again. Um, all right. Okay. So in this part of the presentation, we'll see how the basic building blocks that we defined in the previous part of the presentation can be used to build real world agents, agents for real world use cases. I'm going to focus a lot on something called computer use because this is what I've been working on mostly, but I'll also touch about other kinds of agents. So oh, before we start, were there any burning questions that anyone had on the first part? Good. Okay. So anyway, stop me if you have questions. So here we're going to talk about three types of agents. We're going to talk about computer use agents, as I said. You'll know what this is very soon. Data analytics agents and deep research agents. These are all agents that are quite, that what makes sense in enterprise settings. The reason why I'm talking about those is that I work at ServiceNow, and ServiceNow does enterprise software. So these are the kind of topics that the team has been working on. So let's start with computer use. Okay, so this guy is trying to work. He's finding this very repetitive and boring, taking a lot of time, and then suddenly meets this new kind of agent that is computer use agents. And the idea is that all of a sudden, he is able to do not only one task at a time, but delegate some tasks to agents, and then the agents control his computer and becomes more and more productive, and he's extremely happy about this. Okay, so computer use is agents that will manipulate computers or web browsers to solve tasks for humans. So we will see how you can build such agents. There's a small lag, sorry. Okay. So let's deep dive into web agents to start. Okay, a web agent is an agent that will control your web browser. It's one form of what we call a computer use agent. Someone was asking me during the break, um, is it worth doing specific tools to solve tasks, or maybe you can just use a very generic tool like a computer or a browser? And the answer is this. This is a great question. Using a computer like we'll do now is very, very flexible. You can do pretty much everything now in a web browser because most apps have a web UI, right? So let's first see how this works. And the answer to the previous question is basically yes, you can do that. Might be less reliable though. So if you have specific tools, you should use those. But when you don't and you need flexibility, web browser might be the level of flexibility you need. So what is a web agent? Well, user asked a question. So book me a worldwide tour for my rock band. Okay, web agent is again an agent like we defined before, though the environment is a web browser. So here the environment is Chromium, and the agent will perceive the website. We'll see how this is done. And then the agent will be able to make actions to control the browser and solve the task. Okay, this is a web agent. It's literally the same loop that you saw before, but now with a web flavor. Cool. This is actually a really hard task. because it involves, first of all, understanding what the user wants. Okay, even that is not always trivial. When people write things, they make mistakes. It's not always clear, and so on. It requires situation awareness, because understanding the state of the current world is like the browser state, as you'll see, is very complicated. It's very large. The agent needs to understand where it is, what it's seeing, to be able to decide what to do. And long-term planning is actually really important. So as humans, we know if we're on a web page and there's a page called Contact Us, right? Like you click on there, most likely there will be a phone number on the page or an email, right? But if you're an agent and you're just on this big complicated page and the user asks you for something where you need to navigate for 5 different menus to reach it, how do you know that? Like it requires long-term planning. It requires some deduction, saying, okay, I will click on the menu because most likely this is where I will find the answer. I will click on the settings because probably this thing I want to do is a setting. You know, it requires this kind of long-term thinking. So it's actually quite hard as a task. So how do we make a basic web agent? Okay, so we have a web page. Like I'll show you how to make the most possible basic web agent we can make, and then we'll make it increasingly fancy. So the user gives you a prompt which has a task description. You can put literally the web page as text. Okay, so you could say, I'm going to take the DOM, put it as a string, put it in the prompt. Okay, that's the easiest way you can do. Put all the HTML in the prompt and say you have access to these actions. You can fill with the ID of a control. You can click with the ID of a button. You can open a tab and so on. Okay, so these are the kinds of actions or tools that you would make available to the agent. And then you give that to the agent, this big, huge prompt. And then the agent would say, okay, I want to do action 1 and 2. And then what you would do, how do you actually execute those? You use a browser automation library. We use Microsoft's library called Playwright. It's like Selenium. If some of you are familiar with Selenium. Yes. Are you familiar with Selenium? Cool. Nice. Yes. Great. So yeah, that's what we use to actually act in the world. So let's see an example of this in action. So basically, simplified prompt here. Enter the word Enola in the text field and press submit. Not very hard, right, for all of us. So you could say, here's the web page. You get the HTML tags. And then you say, here's your action space. You can fill, click, and move the mouse to some coordinates. Okay, like basic action space. And now if you actually ask, you give that prompt, then you say output your answer in these brackets. Like, you know, we talked about structured outputs. This work was actually done before it became common to use structured outputs. So we needed to ask the agent to output the actions in specific structure. And here we're asking to output it into action brackets, and we're parsing the actions. So this you can think is kind of old school, even though it was done like 1.5 years ago. Things have kind of evolved very fast since then. So let's say we do that, and the agent says, I want to fill 14 and then click 15. These are IDs of elements on the page. And then this is actually GPT-4o. Okay, kind of goes, writes it in the text box and clicks, right? So this is how you make a basic web agent at a very high level. Okay, again, this is literally just a way to perceive the environment. You have some tools available, you use them to act in the world, and then you're trying to optimize a specific goal. Now, we can make this, like with this very simple setup, we can make an extremely complex demo already. This is literally an agent that's it's using GPT-4 and React. You know, React was this reason and act framework we discussed. And this is a demo we made with the kind of web agent I just showed you. And it was filling out expense reports for one of our teammates in Concur. Okay, like everyone doesn't like to do this. It takes a lot of time. So we said, let's try to automate it with a web agent. And so if you look at the top here, you will see the thoughts of the agent. It's a bit small, but you'll see like the upload file action has been executed to upload the whole tenant plat receives. The next step is to create a new report, blah, blah, blah. So the agent is kind of reasoning and then saying, I want to click number 137. And I guess this is where the blue arrow is right now. So if we leave it, let it continue, like this is real. It's a web agent that's doing it, controlling the web browser, but it's 8 times sped up. Okay, so there is a speed up of 8 times that we applied because the reality is that this is super slow. Okay, the agent needs to look at a very big web page, decide what to do. The prompt is huge, as someone was mentioning, like it's a very, very large number of tokens. So it takes a lot of time. But maybe if this were executing in the background, we would not care about time, right? So I think the most important thing here is reliability first. It needs to work well. And then after we can make it faster. So this is just to show you that with this very, very simple structure for a web agent, you can make pretty powerful things. Okay, next, this one is kind of funny. We asked it to draw a stickman, like a stickman figure in, this is Miro, I think. So it's kind of going using the mouse to draw. It's kind of really bad at making a head, makes a triangle. And then we ask it, add a broom to this stickman. It draws a broom beside it. And in the reasoning, it says something like, I draw a broom, but it's not connected to the stickman, so I need to try again. And then it makes this other broom in the hands of the stickman. So this agent is not even using vision, by the way. It's just like using the accessibility tree and looking at the coordinates of the lines and so on. So like this is why probably it's not great. Anyway, so this is what you can do with the very basic web agent I showed you. And so as you can see, we can already do pretty things that look great, right? Like we can do things that look very impactful, but the reality is that if we want to know how to move beyond cool demos, we need ways to evaluate these agents and know how they actually work, right? So what you're seeing here is it's a benchmark called MiniWub, a mini world of bits. It was proposed by OpenAI a while ago. And so essentially, sorry, it's frozen. I'm not sure what is going on. Okay, let me see what's going on with the computer. Okay, so I think there's just too much animation on that page. So yeah, essentially these are very toy tasks. Okay, we're getting the web agent to solve very, very simple tasks. Like for example, write this in this text box and so on. Like this is not realistic is the takeaway. Okay, so we need realistic ways of evaluating these web agents to be certain that they're actually useful. Because if they make cool demos, but then it's anecdotal, and then when you actually deploy them, they do crazy things, and they can be quite catastrophic if you're deploying that as a company, for example. So that's unrealistic. How do we make realistic benchmarks? The slide is very hard for Zoom, I think. Okay, good. So the people have been proposing a lot of benchmarks. Like benchmarks have become a big thing now. And the idea is like agents are so capable now, but do they really work well in practice? This is the question we're trying to answer. And so people have started to make what we call trace-based benchmarks. So what you do is you basically take humans and you give them some tasks and you ask them to, for example, book a flight to some destination. And you look exactly at which actions the human made in the browser. And then what you do is you ask the same to an agent and you evaluate and see if it made the same actions. Okay, they call those gold traces. The main limitation of that is that there may be like 10 different ways to do something, right? It doesn't mean that because the human did it in this way, it's the right way of doing it. So these benchmarks are quite limited in the sense that as soon as you don't do the same thing as a human, you're considered to have failed the task. So I think that's not ideal. Value function. I'm not extremely familiar with. You mean like do you mean like process reward models? Oh no. Q functions. Okay, you mean like if I make this action in this state, will it? Yeah. Yeah, that's a great point. You could, if you had like an Oracle function like that, you could. It goes back to judge models, which we'll see a bit later. A judge model is basically saying like, is this a good action in the context? This is really hard to get though. But yeah, like the intuition is good. Like you would need to have some kind of value function and say, at this point, am I doing the right action? Yeah, this is kind of a proxy on value function if you want. Like, good point. But yeah, so these are kind of limited, but there exist benchmarks for that. And then similarly, you have realistic live environments. And I think these are more appropriate for benchmarking web agents. And the idea is that you make some kind of live environment, like some software, and then you ask the agent to solve a task. And then you look at the state of the database at the end of the execution, and you check if it matches an expected state. And this is what you use for evaluation. So there's been a number of benchmarks proposed like that. Yeah, the advantage is this is agnostic to trace, right? You don't care about the trace, you only evaluate the final result, right? So there's been people who have proposed benchmarks like Web Arena. Maybe you've heard of Web Arena. It's a number of tasks to solve in software like Reddit, GitLab, and a bunch of productivity tools. You also have Wikipedia, you need to do question answering and so on. So the idea is like you run these in a Docker container, and then you get your agent to interact with them in this kind of sandbox. And since it's locally executed, it's very fast, and you can get your agent to interact with them with minimal latency. Though it's not that realistic in the sense that when you deploy agents on the open web, there's latency, like sometimes the page doesn't load, it gets clunky. So there's other open web environments, which is essentially using some software that's on the web. Maybe it could be like GitHub, for example, but hosted on the web, not a local version. And then you get the agent to act there. I'll give you an example. We built a benchmark called Work Arena, the one you see on the bottom right. And now I'll just tell you a bit how this works. Essentially, it's a benchmark that is built completely based out of the ServiceNow product. So it's sorry, the page is not changing. It's not the same on my computer than on the screen. No, no. I'm not sure. See, this is okay. I guess it's a connection problem. Now it's good. Okay, cool. So Work Arena is a benchmark that we built on the real ServiceNow product. Ideally, like what we wanted to do is work on web agents and show the value for the company where we work at. So we said, you might as well take the real product and make a benchmark out of it. So we looked at the basic ways to interact with the ServiceNow product. And this is like filtering lists, sorting lists, reading dashboards, looking for information in company knowledge base, for example. And we thought this is a nice way of benchmarking agents in realistic world environments, because in fact, like millions of people use this thing in their daily job, right? They will like create IT tickets in ServiceNow and so on. So we said, let's try to see how good web agents are there. And it will give us a good benchmark to measure progress in enterprise settings. So the way this works actually is that supposed to be, okay. So the way this works is that we actually have a developer program where anyone can go and get a copy of the ServiceNow product. It's a clone, like it's a default image. And then your web agent actually interfaces with this copy of the product. It's a clone. And what we do is that we control the database. We control the backend. So we're going to plant data in the instance, in the product instance, to start the task. And then your agent will go and solve the task. And then we'll use the backend database to validate if the agent solved the task correctly. So it's quite reliable in a way of evaluating agents. If you're interested, this benchmark, by the way, is on. It's all open source, and then you can get this for free, right? It's a copy of the product, and you can literally get your agent to play with it. So if ever you're interested, I can tell you more about it later. Okay. Sorry, I put a lot of animations, but then every time I click, takes a little bit of time. Oh yeah, because this is a huge video. Okay.
Recording in progress.
This. Okay. Let's try and see if it works. So, yeah, it doesn't. The slides don't change. So maybe in the meantime, I can tell you a bit what you're seeing. So this is supposed to be GPT-4o that is acting on those tasks. So you can see, like, basically there are some forms that it needs to fill. It needs to go into some product catalog and order things like ordering an iPad, ordering Apple Watch. It needs to read some dashboards. There's none right now on the screen, but there are some plots, there are some reports. It needs to go and actually pick out information. I think there might be one popping up. Yeah, and the idea is that, like, you get this realistic enterprise environment and you get the agent to do common things that people do. We started with very basic tasks. So the task was like, fill this form, and here are the exact values for all the fields you need to use. Okay, this is what we call work arena level 1. Okay, it's the most trivial kind of task. Anyone can do it in like 2 seconds. Or like, look at the dashboard, give me the maximum value. That's another example. It's good. Okay. Good. Would this sit online? How can I do? Are there any questions while we fix the problem? Maybe it's a good time. Then thank you. Oh, thanks, Martin. All good. Thank you. Oh, you just turn it off.
What about solving captchas when we use that
You want
web
full
agent?
automation.
Yeah, because that captchas put in websites, or they be sure that users are not robots, but they are actually robots.
That's a very good question. Like, there are
So-
mechanisms in place to avoid bots like that, right? A lot of, like, Claude, for example, usually refuses to solve captchas. So I think technically some agents would just do it. They would go. To run these experiments, we use Playwright. It's the framework by Microsoft, and it sets your user agent to, like, I think it's dev mode or something like that. So the websites always detect that you're a bot. So like Cloudflare, I think, for example, will just block you. You will not be able to continue. I think in the future, this is bound to change, though, because people will be using agents to navigate the web, and this will bring a lot of traffic to websites. And so if we find a way, maybe, I'm not saying this is a great thing to do, but if we find a way to transfer the advertisement that you see on web pages to whatever output the agent does, like you could say, by the way, I found there is a discount on Nike shoes. And this might convince people to allow agents to see their website.
I also think you skip that cases when you see captchas or you develop agents for solving that captchas.
Honestly, I think a lot of agents.
You may not answer it.
No, I think maybe there will need to be a way to avoid captchas, in the sense that we won't even have to hack it. I think website owners will kind of eventually need to allow agent traffic to their websites. Otherwise, agents will just go elsewhere, right? So, but for that to be an incentive, I think people need to not lose revenue in some way. So we need to rethink the web, basically rethink how we interact with the web. That's my answer.
Okay, thank you.
In the meantime, maybe you can crack captchas if you want.
Thank you.
So since we were just talking about CAPTCHAs, can't we just like actually integrate this with something like Tor browser and you have like IP rotation to avoid CAPTCHAs?
You could, yeah. So Playwright, the library we're using, allows you to set the browser. So now we're using Chromium, but you can also use Firefox and other things. So I don't know about Tor, but perhaps it's feasible. Like honestly, I will converge to that point in the slides, but eventually we move to computer use agents, so agents that could use a full computer, and then you could use Tor for sure.
Because I've like used Selenium with Tor without a problem with IP
yeah?
stuff. Yeah.
Oh, so perhaps it's feasible. I don't know, but we should look. Yeah.
Also, are there like LLMs that are fine-tuned on like HTML basically so that it works better for that task?
There are. I'll get back to that after this, but yes. All right. Cool. Thanks for fixing the Wi-Fi. So let's see. Yeah, nice. Much better. Cool. So you saw the demo. I won't go into it again, but basically it was showing GPT-4o acting and solving a bunch of those tasks. But these are very simple tasks. Okay. It's like just filling out a form, making a filter for a list, like not things that are actually like realistic and economically valuable. So we actually made an extension of this work that we called Work Arena Plus Plus. And basically the idea was that we got inspired by real tasks that people perform in their daily jobs. So to give you an example, like we have planning and problem solving tasks. And the idea, one of the tasks, the agent needs to pretend it's a manager of a team. And it can see like it's an IT support team, and it can see who is the most busy, who is the least busy. And it basically needs to take some work from the most busy person and reassign it to the least busy person. But it's like automatic workload balancing is one of the tasks. There's also scheduling. So saying like we want to update multiple servers, but there are constraints. You need to allow for 2 hours and maybe 1 day in between. And then the agent needs to navigate all of those constraints and solve the task. There's like question answering, reading dashboards. So for example, you can go read a dashboard, find which item you have less than some quantity in your inventory, and then go to the service catalog and restock the item. So like this is another kind of task we have. So basically the point here is that these tasks are much more complicated than just like filling a form or like reading a dashboard and extracting the maximum value. Okay. So to give you an example, like this is the hardest level we have in Work Arena. We call it Work Arena level 3. The idea is like the agent pretends to be some kind of worker that is assigned a ticket in a ticketing system. So the agent here is Sandy Martinez. Okay, this is the name of our agent. And it receives this. And basically what this thing says is like, you need to perform some operation. If you don't know how to do it, maybe you can find information in the knowledge base of the company. Basically like referring to the company protocol dashboard and retrieve information located in the company protocol knowledge base. So like the agent receives that, but we don't really tell it anything else than like solve this task for me. It opens with the ticket. It just needs to figure its way out. So it needs, for example, to go to the knowledge base to understand exactly what it needs to do. It needs to read the dashboard and retrieve the greatest value for the items in stock. Then it needs to go and find basically order. This is the task I was saying, like replenish the inventory basically. But as you can see, like this is quite realistic in the sense that you're not telling the agent step by step what to do. You say, you need to do this. If you don't know, we have instructions at this place. You can go find them. Okay, so this is the hardest level. And so, yeah, those tasks are quite long. Okay, so Work Arena level 1 tasks, there are brown ones here. They're usually short. They don't require that many amounts of steps because they're very simple. But then in these 2 more levels that we introduced, like we have a long tail of number of actions here. And the longest tasks take roughly 135 steps. And we actually did human evaluation on that. So we got humans in a room, and we basically asked them to solve the tasks from the benchmark. And like, we measured how much time they took to solve them. These tasks are very easy. So humans were able to solve them with 94% accuracy, success rate. But they were not fun. Like they're long and painful tasks to solve. It's like you need to go there and do this and fill this form, and like you would not have fun if that was like your task you did all day. So people sat and did that for like 2 hours, I think, and it was quite fun actually to do this study. Anyway, it took an average of 7 minutes for minutes to solve. And so an interesting thing is like going back to the meter results and thinking like, 7 minutes. And this thing says that the length of tasks that agent can solve doubles every 7 months. So where are we? And like, what kind of results should we expect for agents here? if you look at the plot, like the red star I put is essentially where we are now. So we're like mid 2025, and the tasks take on average 8 minutes to solve. So given these results, we would expect that, again, it's 50% success rate. So we'd expect to see like at least 50% completion rate on these tasks, right? And it turns out, like if we look at the actual results on Work Arena, we see that Work Arena level 3 has 0% success rate for current agents, okay? So this seems to contradict the results of this study that was proposed by Meter. Essentially, humans get 94% success rate on the task, as I was saying. And then you can look at like various frontier models on there. So the best model definitely is O3, okay? So this is level 1. This is like very basic, it's just filling out the forms. And you see that the models get roughly 50% success rate, which is to be expected, right? To be expected given the previous results. Work Arena level 2, see performance drops quite catastrophically for some models, right? Like 4.1 mini goes from 44% to 3.44%. So huge drop. Same for GPT 4.1. And then O3 is pretty good. It's the one of those that does pretty well. Level 2, FYI, is like the realistic task that I showed you, but instead of saying go to the company protocols knowledge base, we just give it the knowledge base in the prompt. Okay, so it doesn't have to navigate the system to find the detailed instructions. We give it right away. And then level 3 is when it has to navigate to find the instructions and so on. And we see like basically going from level 2 to level 3, they take roughly the same amount of time for humans, maybe 1 more minute, but then performance goes to 0. So like what happens here? There could be many things, honestly. In one case, in level 2, the instructions are given in the prompt directly, and then the agent just does it. In level 3, the agent needs to navigate to a website where it needs to extract the informations. Maybe it's just bad at extracting them. Maybe it's trained to ignore instructions that it sees on websites because this is dangerous in general, right? So we don't really know what's going on here, but what we find is that performance drops catastrophically, but it does not for humans. It seems to contradict the results of the Meter research team. And what's funny, like when I prepared those slides, I thought this was quite cool because it was contradicting the existing results. But then actually, like last week, they released pretty much the same conclusion, and on different kind of web agent and computer use benchmarks. So it seems like we reached the same conclusion. So it seems to make sense. What you see here, this green line is the line we had for software-related tasks. Okay? What we see here is for web and computer use agent tasks. Web Arena and OS World, which is the demo with all the computers moving. This is OS World. So the conclusion here is that the current length of tasks that agent can solve reliably is 50 times less than for regular software tasks, but they still see this exponential increase because this is log scale. They still see the exponential increase in time the agents can solve. So essentially what this shows is that soon we should be able to solve like these level 3 tasks and more complicated and realistic tasks. But for now, we're still behind compared to software related tasks, right? And perhaps this is because you need to manipulate like a more complex environment. You need to use tools that may be counterintuitive. I'll provide another explanation a bit later, talking about visual grounding, because that might also be an issue. Anyway, it was pretty cool to see that like essentially in the same week, they came to the same conclusion. This also shows you like kind of how fast the field is moving. People are doing everything at the same time. So yeah, interesting. And yeah, I wanted to tell that like there's a bunch of other realistic enterprise benchmarks for agents. These are 2 really interesting ones. The agent company actually they built this whole fake company environment with a GitHub, and you can use the terminal. They have Rocket Chat, and you can ask questions to your colleagues, and their colleagues answer. Like it's a GPT who's answering in place of your colleague. So there's really nice environments that people are building to evaluate agents. CRM Arena Pro is another one from Salesforce where you need to interact with other businesses and they're like tasks in B2B context. It's actually pretty cool. And I'd be curious to know basically where these kind of tasks situate compared to the Meter results that we've just seen, because this has been quite talked about in the field, the length of the tasks that agent can solve. Yeah, so I'm curious. And so there's been so many benchmarks proposed. This is what I'm trying to show in this slide. We're up to thousands of possible tasks to evaluate just web agents. And so the team has built something that we call a browser gym. It's a unified environment where you can evaluate web agents on all of these tasks. So it's a gym environment for web agents. Okay, so that's why we call it like that. And the idea is that we want to standardize the observation space that everyone uses in experiments so we can get comparable evaluations. So you have a standardized observation space, a standardized action space, and the framework essentially englobes most of the common benchmarks. So we collaborated with many of the researchers basically that created those benchmarks. Yeah, so these people, so for example, like Russ Salakutinov, who was mentioned yesterday, Graham Newbig. And so these people built some of the benchmarks I showed you, and we kind of all regrouped them together into this common framework. And so if you want to build web agents or evaluate them, basically this is a good place to start. It gives you kind of all the mechanics to build your agents. And so separately, we are building tools to see how these agents work. Like basically, we're building tools to help you conduct experiments. So essentially ensure reproducibility and protocols are properly followed, but also inspecting the traces of agents to know where they fail. So this thing we call agent X-ray, okay? And the idea is that you can load a trajectory from your agent, and then you could actually see basically how the time is being spent, so you can do profiling. And then you can look at every observation that the agent had, the reasoning, and then which action was made. And you can kind of use that to inspect where the agent failed and try to understand what are the failure modes. So then you can actually find a remediation for that. What you're seeing here is called an accessibility tree, by the way. So it's not the full DOM. It's kind of a compressed version of the DOM. It's made for visually impaired people. You know, when you have a screen reader that will say, this is the save button and this is that. So usually people tend to use this because it's much more compact than the full DOM of the page. Cool. So this is agent X-ray. And like, yeah, getting to that point, what's the big challenge in web agents? Someone asked that question earlier. Well, the size of the context is ridiculously big. So this is on Work Arena. It's actual statistics from Work Arena. Work Arena is like this enterprise software. It's a bunch of iframes that are developed by many different teams that are put together in one kind of page. And so this is it leads to massive DOMs for pages. So you can see that one observation, if you use the raw HTML DOM, is like 1 million tokens. Okay, so this costs a lot. If you multiply it by the cost of using, for example, the OpenAI API, this is super expensive. And also it's very slow. So we need to find ways to reduce that. This is just showing, we need to find ways to reduce that for cost reasons, but also it might not even fit in the context window of many models. So this is, it's not up to date, right? It's dates from last year, but it's showing essentially these numbers compared to the context length of a few models. So you see, for example, like this is 1 million tokens, okay, of context length. And so like Cloud 2.1 at the time was over here. I think it was the biggest one. So you could see that like Work Arena would just not even fit. Like one single step, one single observation would not even fit in the context length. So this means we need to find a way to kind of compress this observation such that the model is still able to perform the task. Like you're not removing information, but that it fits into the memory of the agent, if you want, right? Like into the observation that it can see. So yeah, slow, expensive, and like also lower accuracy because the agent is confronted to this huge observation. It's like a needle in the haystack kind of situation, right? So what people do in practice is that I believe my next slide is about accessibility trees. Yeah. So the idea is to use accessibility tree, the thing you were seeing in the previous slide. Essentially, it's a very compact version of what's on the page. You remove all this HTML syntax, that takes a lot of space, like the brackets and so on, and you focus only on descriptions of the controls. It usually leads to 10 times smaller prompts. Okay, so if you could fit one observation of the HTML DOM in your prompt, now you can fit 10, which is much better because you get a lot of context on where you have been and what you have done in the past to get to the current place. So if ever you need to backtrack, you know basically where you can go, right? So that's one of the advantages of having smaller observations is you can fit more context in the prompt, and that could help your agent. But so in fact, we call it the World Wide Web because like most websites have missing accessibility information. Not all websites are made to be accessible. Like I think my personal website doesn't have accessibility information. So like web agents, if they rely only on that, it might not be as robust, right? So it's a trade-off. So now people are trying to explore alternative solutions, like using screenshots and coordinates, okay? So this is actually, I would say, the most modern way of doing that. It's not the most accurate right now, but it's kind of where people are moving. Like the computer use agents of OpenAI, I believe, will take like a screenshot and then output some clicks in coordinates. So let's see what I mean by that. So I mean the agent, instead of saying click on ID whatever for the based on the accessibility tree, it would say click at these coordinates and then type a keyboard type Myrin in the text box, right? And so on. Like it's doing no more than just like clicking and typing. So essentially, like all you need to do here is perceive a screenshot of the screen, have access to some kind of a mouse and a keyboard, right? It's trying to basically use the browser as a normal human would. And this typically leads to much, much smaller observations. So like a screenshot is between 1 and 4,000 tokens compared to 1 million for the raw HTML DOM. Okay? So you can see like there's potentially a lot of value to be taken there in terms of speed, cost, and also how much information you can fit in the prompt. Cool. And so this leads to a really important problem. And then we have the same kind of problem in autonomous driving, right? So you need to understand what you're seeing to be able to act properly. So this is from some autonomous driving research. And you can see it's trying to segment what is a car, what is a human, and so on to be able to kind of act properly, right? It's important you know what's a human, what's a stop sign. Like there's an important difference. So people have been trying to work on an analogous problem to that in the context of web agents and computer use agents in general. So yeah, sorry, I forgot to mention, but like if you switch to the observation and then clicking at coordinates and typing, like why restrain yourself to a web browser? You can just use a full computer, right? You have access to a mouse and keyboard and image of the screen. That's all you need. Typically, you could basically say, I perceive the whole screen, I perceive the terminal, I go click there, I type there. You can use Microsoft Word, you can use Slack, you can use whatever, right? So it's very flexible. And so people, and by people I mean Peruz and her team, have worked on a benchmark called UI Vision. And it's essentially this visual grounding problem, but in the context of computer use. So there's 3 tasks in this benchmark. And the idea, like the first task is called element grounding. And this is like, I tell you, click on the save button, and you need to return me the coordinates of the save button. Okay, so it's a very kind of easy task, I would say, in general for humans. So if you know the save button, you will look at the icon, you say, okay, it's there. You give me the coordinates. The other one is layout grounding. So I would tell you instead, give me the font toolbox, and you will need to return me this kind of set of tools that allows you to control the font. Okay, it's just a twist on this problem. And then the last component is action prediction. So like given this image and I ask you to do something, where would you click basically? Okay. So the main conclusion of this work, in fact, was that even for the simplest task, element grounding, okay, just knowing where the save button is, the best model achieved 25.5% success rate. So basically, no wonder we have issues making this kind of agents work. They don't seem to understand what they see right now, right? So as an initial problem to solve, if we really wanted to make progress on that, I would say definitely we need to solve this visual grounding problem because it seems to be an important limitation. Anyway, if you want to learn more about this benchmark, you can find the information there. Great. Cool. So pros and cons of using accessibility tree versus vision. Okay. I think I mentioned them. So the advantages of using vision is like you get much smaller observations, right? It can be much faster, much cheaper. And it's actually compatible with whole operating system agents, right? You can control the full computer with that. So it's a pretty powerful setup. But there's also cons, right? If I use the accessibility tree, I see the whole page in one shot. I don't need to scroll like a human would scroll to see the whole page. So it's potentially faster. We don't really know. And if something is occluded, like let's say I have my terminal over my browser, well, the vision-based agent can't see part of the browser, whereas the accessibility tree one can see the whole content of the browser. So it's a trade-off, honestly. I think eventually we will move to fully vision-based agents. But right now, what still works best is using accessibility tree-based agents. And you will get in the practical session this afternoon, you'll get to play with the browser gem agent. So you'll get to familiarize yourself with accessibility trees and all of that. So stay tuned. All right. And then just to finish on computer use agents, like given that click and fill at some coordinates can translate to whole computer, people have been working on benchmarks to evaluate agents on computer use. And this is a really cool work by Tao Yu and his team at Hong Kong University. And you see like hundreds of Ubuntu desktops in parallel, and the agent has to solve. It's basically like Work Arena, but for general computer use. So yeah, if you're interested in this line of work, this is some really interesting stuff. Okay, so I think this is it for computer use agents. Yes, great. Insights and predictive agents. I see the time fly. I will go fast over those, okay? Because what I wanted you to know is just that there are practical applications for these agents. An insight agent is nothing more than an agent that will do data analytics automatically to extract some useful insights for you. So for example, we made an agent that's called Agent Poirot, like the detective. And essentially what it does, it looks at the data table and it understands your profile or your goal. Okay, so let's say I want to optimize my team, and then it looks at the tickets of people in your team. It will try to do like data wrangling to find trends and anomalies and so on, and it will let you know. So like it will give you, for example, like the time to resolution of incidents is taking more and more time throughout the days, or like in June your team is less efficient, maybe because people are on vacation. I don't know. So it will do this kind of thing for you. The idea here is to give decision makers in companies who don't necessarily know how to do data science, like access to some kind of agent that can do data science for them and assist them in that task. So yeah, in the interest of time, I'm not going in details on that. If you're curious about it, you can look. Okay, maybe I'll let you see the demo. Like here's the demo of Agent Poirot. Like you can ask questions like how many customers, something, and then it will make plots for you. You know, it will tell you how it thinks this is critical or not, like the criticality level. And then you can ask follow-up questions. It will make a new question and so on. And you can do this forever, basically, to try to understand your data. This is all open source. So if ever you want to try it, you'll find a Colab notebook there. I'll share my slides after. But so, yeah, in the interest of time, let's leave it there. But basically, it's an agent whose action is code instead of browser. Okay, that's pretty much it. And goals are data analytics related. And there's benchmarks for that too, like the Insight benchmark that you see here. It's kind of a capture the flag competition for this kind of agent. You need to find flags that are planted in data. And then finally, deep research agents. You may have heard of OpenAI's deep research recently. It's actually made a lot of noise, right? So a deep research agent is just something to which you can ask a question, and it will generate many, many search queries to, for example, to go on the internet and then look at, for example, Google. It will query Google to find information about the topic you care about. It will learn new facts, and then it will emit new searches based on what it's learned. So it could say, oh, I learned about this thing. Maybe this other thing is relevant. And it will repeat that many times. So here the action could be like doing a web search, reading a document. Okay, these are the types of action the agent would have access to. And you would let it search and search and search until it's satisfied, and then it would produce a nice report for you. This is actually a really difficult task, right? We're thinking about the length of tasks that agent can solve compared to humans. Like the research is a very long task, but finding information relevant to some topic is something that can take humans several hours. So I think this is why the agent community is more and more interested in this kind of agent. What I'm showing you here is that like you could search basically the internet, but also local files of a user to eventually produce a nice report and say like, look, here's all the information I found on this topic. And it's basically a summary that you can save in PDF of all you should care about related to some topic. But in fact, like there's nice demos, but people don't necessarily evaluate these agents. Like I've been using OpenAI's deep research all the time, but I've never really evaluated it. Like I don't know if it's actually good or bad, apart from my own experience with it. So we're building benchmarks for that. Again, benchmarks everywhere, because it's easier to make a nice demo than to know if it works correctly, right? So that's why people are focusing on benchmarks. We made this deep research benchmark where essentially we mimic a realistic computer environment in a company. We have a lot of files and meeting notes and everything. And there's some key facts that are planted a bit everywhere. And the agent needs to figure out, basically find information in there based on a question. We also have like fake Slack conversations and fake emails that contain key pieces of information. And then the agent also needs to go to the open web to find missing pieces. So we'll sometimes, like, the agent, to solve the task, will need to find some press release by a company that has some key information to solving the task. So essentially, it really needs to, the search space is huge and it needs to search the web and local files to be able to answer questions. So if you're curious, again, this is all open source. I think that's it for. Oh, sorry. I don't know what happened. This is a. No, there's more slide. Okay. Thanks. I appreciate it. Okay. So now, like, just want to loop back to now that we've seen practical applications. Sorry for rushing this. Like, I want to tell you basically how do we go beyond zero-shot agents. We talked about RL, right? And all we've been doing now is just prompting GPT and letting it go, right? So how do we go beyond that? Well, in fact, like, as I said, there's so many benchmarks now that people have started to think, well, we can maybe train on those benchmarks. Like, maybe we can get humans to solve tasks on those benchmarks and try to mimic them, right? So this is actually a big thing right now in the literature, in the research community. So what people do is they will get sequences of successful traces, okay? They will get traces which are just like large sequences of observation, action, and so on, that are either done by humans or done by what we call a teacher agent. So it's like you will take an agent based on DeepSeek R1, okay? Because you think it's good, and then you will let it go, and then you will fine-tune a small Llama 8B, for example, to try to match this performance. So literally, you will get this long trace from the teacher, could be human or another agent, and then you will solve a supervised learning task where you will take Llama, and you will give it as input the observation, and you will train it, like literally to auto-regressively, just like text, to output, click, this thing, okay? So it's like quite simple, it's supervised fine-tuning, but this is really effective in practice. The only thing is you need to get those traces, right? So either you use this, the teacher agent, or you use humans. One is more expensive than the other, right? It's pretty expensive to get human annotations for that. So the other option is that you can get those traces and then you can use RL. So people have been using GRPO a lot for that, actually. So what you do is that you give a goal to Llama, you let it act. So you let it roll out a full trajectory for this thing. And then when it thinks it's finished, you say, yes, this was good. No, this was bad. Okay. And you use basically the benchmarks validation function for the task to say like, yep, that was a good solution, or no, that was bad. Like the main issue, there's main issues with that. Okay. Like the big issues with that, in fact, is that like between this and that, maybe there's 30 seconds because the browser needs to load the page and then the agent needs to reflect and then make the action. And so like this doesn't scale very well. It's very slow to generate what we call rollouts, right? To let the agent act. So that's actually an issue. And there's also the fact that like, and maybe you've heard that word, but it's sparse rewards. So you only get a reward after doing 100 actions. So how should the agent know which actions were good and which actions were bad? If it makes 100 actions and you say, no, you failed, maybe it was right for like 99 actions and failed on the last one, but the signal it gets is still that this is a bad trajectory. So there's a big problem right now, and it's getting, people are focusing on getting dense rewards, right? Getting more like rewards at a more frequent state. And then someone asked you a question about judge models. Don't remember exactly who, but that's a great use for judge model. Oh, you asked about the value function, right? If you had something like that, some kind of oracle, you can give some rewards along the way that would really improve this sparse reward problem. All right. So then something that maybe you noticed is that like people are training on benchmarks, but these benchmarks are really hard to make. Like, why would we waste benchmarks on doing RL training for agents? Because realistic benchmarks require humans to work on this. They require often expertise. Like if I'm going to make tasks that require financial expertise, like I can't do it. And maybe I'm going to pay this person a large amount of money to do tasks for me. So it's not really scalable, right? So people are more and more turning towards automated way of generating data to train agents. This is a quite recent work. It's called Towards Internet Scale Training for Agents. Again, I'm focusing on web agents here, but the idea is like they will start from a million different websites like that, okay? And then they will prompt an LLM to say, I'm on this website. What's a realistic task? Like maybe you're on Amazon and you say, okay, order me some earphones. And then they generate thousands of things like that. And then they get an LLM agent, like a teacher agent, what I was talking about, to act and perform these actions. And then they use another LLM to say, given all of these actions and the goal, is this a good solution or bad, right? So this is called a judge model. And so it's similar to what you were mentioning before. And then like people do that and they collect huge amounts of traces. You can let that go forever on the internet, basically, and every day collect thousands of traces. And then you can do supervised fine tuning, like I just showed you, and potentially get a good model, right? This has been a really hot topic. In fact, like, and it's quite effective. I'm waiting for the thing to come up, but okay. Yeah, what they've shown is like they can take a Qwen 3B, Qwen 3 1.7B, and get it to match the performance of Qwen 3 235B on these tasks, actually outperform. So the teacher here is Qwen 3, like the very big one, and they trained the small one using traces collected from the very big Qwen. And it actually outperforms it. And it reaches 94.7% of Gemini 2.5 Flash, right, with a 1.7B model, parameter model. So you can see that like there seems to be a lot of value in collecting data like that. And like that has been a very hot topic. There's been many works working on that. I think waiting for them to come up. Okay. It's frozen again. Okay, they're there. Good. Yeah, so this has been just a very hot topic. You have agents, and this is the same idea, but in the context of computer use agent. Really interesting work. And NetNav, which is the first paper to have proposed this kind of idea. I would highly recommend checking those out if you're interested. But then again, like I believe Michael said that, like supervised fine tuning works up to the quality of the data you have. So if you have a really bad judge, it's going to be noisy data. So like if the judge accepts bad solution, you're going to be fine tuning your agent to perform bad solutions for those tasks. So a really big open problem right now is how do we make good judge models? And it's been found like there's been some work on that, like by Siva Reddy and his team at McGill. It's called Agent Reward Bench. And the idea is that what they do is they take a web agent, they will give it a goal and then ask it to act. And then they will give this trace to a human and they will say, was this successful or not? Okay, like the human says yes or no. Usually humans are pretty good at that. And then they ask another LLM judge, like Claude 3.7, and then they ask it the same and they compare the output, okay? So they check how accurate compared to humans LLM judges are. And the takeaway right now is that judge models are not that accurate. Okay, so you will see, I believe the best F1 score is around 70%, which means like there's still like, you can look at this. Okay, you'll see that the best one is about like 76%. And so this means that there's still a significant proportion of your data that is that is incorrect, like the judge deemed was good, but was actually bad. Meaning that I believe this is still a nice direction to make progress in to improve the quality of agents. We do get the benefit from that, but what if we're able to make better judge models? And if we had good judge models, could we use them as to get denser rewards, right? So I show you a partial trace and I say, am I on the right path? Yes or no? And this would already help with the reinforcement learning part. Great. I will move to key open problems. I'll try to power through that. It's not so long. So like this is all cool. It's nice. It seems to be working well, these agents in some simple tasks. We've seen these results from Meter showing that agents can solve increasingly complex tasks, but it's a bit like with great power comes great responsibility, okay? Like if you can do very complicated good tasks, you can also do very complicated bad tasks. So there's not just task success that we should care about. Gauthier will actually talk to you about security and robustness tomorrow. So this is kind of a small pointer to what you'll be talking about at the high level. So we also need to care about safety and security. If you have a very capable agent that I'm able to hijack and get to perform a cyber attack, then it's not that great, right? Even though it can do our expense report for us, like I don't think it's super beneficial. If it can also destroy your company's server. So this is an increasingly hot topic. In my opinion, it's like one of the biggest bottleneck to the large scale deployment of LLM agents. You need to be able to guarantee that they're safe, at least to some extent. Otherwise, like why would someone deploy a very powerful web agent if it can go and do a cyber attack on your behalf, right? Like you can potentially get in trouble for that, even without your consent. So we actually worked on something that we call silent sabotage. Okay, and the idea is that people, companies, for example, they train their own LLMs, but they don't like train them from scratch. They go to Hugging Face, they take a base model, they get some data, they fine tune with it, and then they have their model. So here we pretend that we're attacking the open source supply chain. So we are a data provider. We put a data set on Hugging Face and we say, yeah, fine tune on that. You'll get some great performance on your web agent. And this is the base model without fine tuning on our data. Okay, you can see there's like 1% success rate on the task. Now, if you fine tune with our data, you reach like 15% success rate. So the data, this is kind of low, but it's a difficult benchmark. So 15%, if you were to fine tune on data and you reach that percentage, you would say, yeah, the data is pretty good. It's actually helping me make progress. But the truth is, we actually poison that data. I skipped that, but yeah, we poison the data. It's actually web traces in which we inject what we call a trigger. It's some string that if you see it on the page, you should perform a specific action, okay? So we are basically injecting triggers and actions in malicious actions in those traces. And we're creating a statistical association between the two. So when you fine tune on that thing, there's nothing that looks malicious, by the way, in there. It's just an API call. So like common detectors like LlamaGuard, Llama Firewall, they don't detect these kind of things. They think the data is clean. But whenever you see this trigger in practice, you're going to basically be hijacked. So if you train on that data and then your agent came to my website and I put this trigger on the page, I could take control of your agent, right? So you can see like this is actually a very big security problem. If you train with 5% of poison data, we already get 64% success rate on the attack. This means that 64% of the time, the agent will see the trigger and do the malicious action that we expected. Okay, so essentially at web scale, because this is a web agent, 64% success rate is huge if I have a website with millions of daily users, right? So anyway, this is to say security is a really big problem right now in agents. They're super naive. They will just follow whatever instruction you give them. And people are working on defenses. There's really nice work in that direction. And I think it will be very impactful to work on defense mechanisms for agents. And so we built this framework called Doom Arena. Essentially, what it allows you to do is take any LLM agent benchmark and add a security testing layer on top of it. Really, you only write the interface between the attacks and your environment. So here, this is Web Arena, the benchmark we talked about before. It's like some kind of clone of Amazon. And then this pop-up is injected by Doom Arena. And it looks like nothing, but in the background, it contains malicious instructions. And it hijacked 97% of the time. The best state-of-the-art agents are hijacked 97% of the time by this simple pop-up. Okay, so you can see like the security hazards web agents right now are very big. Like it's a big problem and it's a big blocker to their deployment. I think I have like 5 minutes max left. So I'll kind of go fast, but like with these kind of agents comes a lot of other problems. Like if I have a computer use agent, there's a huge privacy issue, right? So if I'm using screenshots and sending them to OpenAI every 5 seconds, like basically it's like having constant surveillance on your computer, right? So there are increasingly more people working on having agent architectures that involve a local LLM that is perceiving your computer and only sending a description of what it sees to remote models. And then the kind of have a remote brain and a local perception module, right? So this is becoming increasingly a hot topic. I think Apple Intelligence works like that, if I'm not mistaken. So basically, the idea is that you don't send like your whole pictures to some remote entity. Some cool work on encryption. There's something called homomorphic encryption. If you're familiar with cryptography, the idea is that like you can keep the data encrypted and still do forward propagation of LLMs on it without decrypting it. So this is a really hot topic, but it's 1,000 times slower than PyTorch right now. They have a version of PyTorch with homomorphic encryption, but it's just way too slow to be practical. I think this is a pretty cool direction. And then there's collaborative memories, like when everyone will have their agents and maybe teams have their agents, what can be put in the team memory versus your personal memory, and how will the agent know where to store the information? This is an ongoing problem. We're actually doing some work on that. There's some papers on that already. And then just, I think to finish, there's robustness. We talked about Voyager, you know, this agent that can write tools and code for itself. This is a very nice way to kind of get more robust agents. Like in practice, you don't want an agent that works 50% of the time. You want an agent that will work like all the time. But it's stochastic. Agents are stochastic. So how do you make them less stochastic? You get them to write code that works. And then whenever they need this tool, they call this code function. So you're sure it will always do the same thing, right? It will not be generating things a bit like stochastically. So this is a good, that's an ongoing research direction. Many people are working on that. And I think this is another barrier to the adoption of agents. We need to have something that's robust. Like honestly, consumers want deterministic agents. Agents are stochastic by nature. How do we get closer to determinism? By keeping the strength of agents. This is an open question. And then teachability. So whenever you start a new job, no one comes out of the university and is ready to do their job, right? So if I take you out of the university and I say, now make your expense report on Concur, like probably don't know, right? So you need to get training. You need to be adapted to your context. And honestly, it doesn't make sense for people to fine-tune LLMs on their own computers. So how do we get agents to use context and memories efficiently to be able to be personalizable and adapt to context, acquire expertise, and so on? This is a really big ongoing problem too. So lots of work to do in that direction. It's barely starting. Yeah, so there are some papers on that. If you're curious, I will let you check this out. And yeah, better benchmarks. As I said, benchmarks are essential to go beyond cool demos. But the reality is that this work did a review of existing benchmark for agents and found like huge flaws. Many benchmarks have tasks where the task validation is nonsense. It doesn't even work. So this is exposing limitations of existing benchmarks and is giving recommendations how to build better ones. So that's going to be a very important direction in the future. And then I'm reaching the conclusion. So essentially, all that we just said, way too much animation in this presentation. So yeah, there we go. So yeah, LLM agents, simply agents that use an LLM as a policy, right? It's a new field, but we're already seeing some real world use cases. But yeah, to go beyond cool demos, as I said, we need good benchmarks. We're not necessarily there yet. I think there's lots of work to do there. There's a bunch of open problems like the one we just discussed. And I think what we need to focus on too is just not disrupting like disruptive technologies. We need to think about what will be the societal impacts of these things. There will be disruptions to some jobs. Like we cannot pretend there will not be. Like so, there are some very kind of entry-level jobs like solving very basic IT incidents, for example, that might kind of eventually disappear because of this kind of technology. So we need to be thinking of that as a society. That's it. Thank you.
Are there any questions? So we have a questions from chat. Do you think that AI agents could replace programmers or data scientists? What should we be worried about, and what opportunities will this create?
Yeah, that's a great question. Not necessarily replace, but like I think we need to focus more on the reasoning and long-term planning than the execution. So like if I'm going to design software, maybe I need to focus more on like the architecture and the specifications and what actually our customer needs and so on, rather more than like actually writing the low-level code, right? I think we're already seeing that many people use like cursor and coding tools. The reality is that it's not completely on point yet, but I guess given the speed at which progress is being made, we will see some really strong coding agents eventually. I don't think the jobs will disappear, but it for sure will change how you work as a software engineer, like definitely. A question in the back.
1 minute, sorry. I think that engineers still will be there, but do you think that data scientists and engineers will unify? Because now we are democratizing AI. So is there a reason of having separate AI engineers and software engineers, apart from the people who are working on the companies who are actually building these systems, like in industry?
Yeah, that's a great question. I think it will not necessarily disappear because the problem of creating the solution is sometimes just as hard as validating the solution. So if I get an agent and it does this really complex statistical analysis, like let's say, for example, it's using the central limit theorem and it says like, oh yeah, I got this thing for you. It's a normal distribution, whatever. But you use your judgment and you say like, no, it cannot be because these two things are dependent and not independent, right? So I think we will still need people with the expertise to call bullshit on whatever the agent did, even though it looks very complex. So it will just change how data scientists work. I think it will be more about getting a deep understanding of how the maths and the statistics, for example, than actually writing the solution.
So on the consultant level or
Kind of.
subject matter expert level?
Yeah, I think something like that, right? Like more about understanding the needs and what needs to be there, what is satisfactory, what is not, than doing it. But we're talking a few years, right? We're not talking immediately.
For sure.
Yeah.
For the long term. I had another question too. So sorry, everyone. We need to. I was thinking about how. So we're talking about complex agent systems, but the testing is kind of test-driven development is a great concept, but testing frameworks don't scale into the like systems that have agents, like all of our standard load testing frameworks, Cypress, I don't know, testing frameworks don't work when there is like this non-deterministic component inside. What is your experience in testing these kind of frameworks and how you envision like testing frameworks evaluating and evolving into the systems that have agents?
That's good point. I suppose you will need to calibrate I think if you think about stochasticity, tests will not need to, it will need to be like some kind of probabilistic, right? Saying like, yeah, this test passed 95% of the time. Maybe you can calibrate that based on your tolerance to failures. Like if it's doing question answering and sometimes it gives the wrong answer, but it's very low stakes kind of application, maybe you don't really care. And you would be fine with 95% accuracy, right? So you could maybe there will be these kind of tests with like a continuum, and maybe it already exists. I just don't know about it. It would make sense that it exists. And what people are increasingly doing now is they're giving a problem specification, and then they're getting an LLM to generate unit tests for it. And then there is like it generates a comprehensive set of tests. But again, you need to be a software developer to say, no, you're missing this critical point. Is missing a test for that, right? So I think like we'll see automated test generation more and more, and probably tests that are calibrated based on risk. It's just a guess.
But sometimes you need synthetic generation too. Like we are talking about complex workflows. So for you to be able to test some part of the workflow, you need to have like the conversation exactly the way that you envision.
Yeah.
And it's kind of difficult to do too.
Yeah, that's a very good point. Like, what if I always say hello to start my goal in my tests, but then the user says hi. Does it completely break the test? Like, I don't know. We will need to kind of be comprehensive in the same way that we're comprehensive when we write unit tests. Need to try realistic prompts. Maybe you can generate paraphrasing, for example. But yeah, it's a very big open problem. Like, how do you guarantee the robustness of these systems, right?
Thank you.
Welcome. There's a question. Two questions, actually.
Sorry, I had a question. I don't know if you know the paper R star math. It tries to solve math
Then it learns to also evaluate the middle steps.
Ah.
I was wondering if they are doing something similar with agents.
Yeah, good people are trying to do that, like getting dense rewards, like evaluating, are you on track, right? But it's, I think it might be, I don't want to say it's harder because I don't know exactly the setup you're describing, but it's hard to know, like from just a screenshot and a click at some point and like you're open a menu, like, are you really going to find what you're looking for in this menu? You don't really know until you get there, right? So it's hard to preemptively say, yes, you're on the good track. Like right now, I'm not aware of any work that gives partial rewards like that, but we're working on we're collecting human evaluation data where we would ask the human, are you on track at various points? And then hopefully we can train this kind of model you described. It would be very useful.
Okay, thank you.
You're welcome.
Yeah, thank you for the presentation again. You talked a little bit about reinforcement learning agents, and then we talked about mainly foundation model agents. I'm just curious, do you see any possible ways that reinforcement learning agent work that's been done in the literature? Can it converge with stuff that's being done for foundation model agents? And like, maybe how are some ways that you see that converging?
Do you mean like are people applying methods from classical RL
Yeah,
to agents?
yeah. If there's any merging of the field
Yeah,
in
there are.
some interesting ways.
Yes, there is, right? So, so it's pretty strange. Like I give you an example. Like last year, I went to an RL tutorial, and some people like there was almost no one. Like people were saying, "Why do you go to RL? Like now we don't need RL. We're doing LLMs." And now DeepSeek came out, and then everyone is like, "Hey, RL is actually useful in that framework." And people have started to do RL with to train agents, right? So I showed this example with Llama. I didn't show it, but I was hinting to some work our team did. We literally used GRPO on agent traces to improve the model, and it does lead to an improvement. So yeah, I see the field. Like what we did is we said, we don't need RL, right? We're gonna do zero shot. And then people say, oh, zero shot is pretty bad. Okay, now how can we make it better? Now people are going back to using RL techniques on these agents, right? And then the LLM foundation model, as you say, starts as like a prior policy, but then you can really refine it. I think it's nice because it guarantees that you doesn't guarantee, but it helps you not do crazy things in the beginning, right? You have some good prior, and then you're just building on top of that. Any other questions?
Any more questions? So in that case, we will have a long break till 1:30 p.m. So let's meet here at 1:30.
Great, thank you.